It's for computational sciences and engineering. And as part of this, of all the research activities and training activities within the center, we also perform from time to time several training events. And this actually it's one of the training events. And if I'm not wrong, it's one of the final training events that is via EuroCC. Since the EuroCC now it ends, there might be a new EuroCC from the next few years. But this is probably one of the last training events. And the idea today actually is to be introduced in what we call ab initio quantum mechanical methods, and especially in density functional theory. So this will be now the main task of the forthcoming presentations. I will start first with a very, very generic introduction in the field. So I apologize in advance because for many of you, this might be trivial, or you might know all of that. As I was saying, so the plan is that in the next lectures, you will become familiar with what we call here density functional theory, and actually with also hands-on session involving Quantum Espresso, which is one of the most popular open source softwares for performing ab initio simulations. That will be the task for the coming. Sorry, Spiro. Yeah, please.
As the actual.
Yes.
Because we are meant to share the screen, because the participants only see the small window.
Which is the small window?
Like this page instead of the presentation.
Ah, okay.
So now
sorry for that. Okay, let's see now. Yeah. So now it should be okay. So now you see the full screen, right?
Yes.
No, the notes, we don't need the notes. So now, perfect, right? Okay, so please, for the online people, but also for the people who are here, interrupt me at any point. It's really, this is supposed to be an interactive presentation, so please don't hesitate anytime to. But let me also close that now, Spiro, sorry, because we have this thing here. Wait, just give me one more moment, please. Spiro, do you know how we? Here. Wait. Hello. Here. Hide video panel.
here. Hide.
Names validators. No. Hide floating. Okay. Now we managed. Okay. I mean, we'll need some time, but okay. Okay, now we're fine. So this is an overview actually of the presentation. So, okay, so I will shortly discuss the motivation behind what we're doing, and which is part of what we call here computational science and engineering. And actually all the applications that we are mostly focused on refer to complexes we call systems or materials here. Then I'm going to, again, give you a very... Now we're going to have this very often, unfortunately. So I'm going to present then, to give you an overview of the different methods here. Let me see if this is working great. So this is behind the idea of actually multi-scale modeling, which refers to different levels of description and different models practically. As I was saying, the training event, the main training event refers to ab initio calculations. Nevertheless, within this first, let's say, presentation, that's an overview, I will try to give you a short review of all of these methods here, from the ab initio to the atomistic to mesoscopic level up to the continuum description. And then there are going to be two talks by Marios on the basics of electronic structure and theory for solids. That is this part, and also the basic of quantum espresso. And later, Marios, together with Nicolas, they are going to help you with this hands-on several exercises about how we calculate properties of materials using ab initio methods, practically density functional theory via quantum espresso. So again, the main idea and the main goal in general in the field of what we call computational science and engineering, is actually to predict properties. And since here we're talking about physics, chemistry, materials, the idea is to predict properties of the materials, but via in silico methods. So instead of experiments, the plan is to use the computers, to use computational methods, algorithms, as we will see later, in order to predict properties of the materials. Of course, this is a very, very broad field. So the event today, this training event, refers only to one of these let's say, categories in the computational science and engineering that concerns ab initio methods and practically mainly density functional theory, which is one of the ab initio methods. So this is just to give you the flavor of the plan today. But as I was saying, I will start with more basic stuff, and I will give you an overview of what we call here multi-scale or hierarchical modeling across scales. So, but before starting, since we are, sorry for that now. This need to close it all time. Since we are in Greeks and we are a bit obsessed with history, as you all know, I will start you with some very basic or very old stuff. So just to remind you, the theory of forms. Do you know the theory of forms from Plato? I'm sure that you have heard about that during your primary, your high school years. So it's, as you see here, 5th or 4th century before BC. And then according to Plato now, just to remind you here, there is the physical world that we all live here. There is the mental world. Mental world is practically our ideas, our thoughts. It's all our mental, let's say, world. But beside these two worlds, there is another world that according to Plato, this was practically described via mathematics. So that's why nowadays, or at least after Plato, this is called Platonic or mathematical world. And now the theory of forms practically is based on this postulate here that the physical world is not as real or true or timeless as absolute unchangeable ideas. So the main concept of Plato, it was that behind what we see, the physical world, there is this ideas world that is something more unique or more, let's say, real or more true. And this is the Platonic practical work. And of course, the most well-known, probably the most well-known actually analogy in philosophy is the famous Plato's analogy of the cave. So just to remind you again, I'm sure that you all know about that, but just to remind you that according to that, we all live in this world, which is the empirical world, and we are somehow chained here and we cannot see the actual things, but we see only shadows of things. So what we observe here are not the real world, it's not this. It's the physical world corresponds to that here. So we are all somehow chained here in this empirical world. Now, somehow, someone is able to escape from this chain and then escapes from the cave, and then comes back to this, practically to the real world. And then he or she is able to see the real world. And that's the main idea of that. I think it's a very optimistic, actually. It seems initially, okay, not so happy, let's say, analogy, but it's pessimistic from the point of view. It's not pessimistic, sorry, it's optimistic from the point of view that the person who managed to escape, and this is what I like a lot here, through pedia, through actually the education, through education, someone is able to escape from this kind of prison, let's say from the cave. And not only that, but then the person is willing to return back and to help the people to free all the rest, let's say. So, and this is related actually with what we call here the effect of education and the lack of it around nature, so the effect of pedia in Greek. Now, we will come later, let's say towards the end of the presentation again to this concept, but now starting from this, let's say very old ideas, we should say that education and science was proceed for thousands of years practically via two main routes. The first route was empiricism, actually, and this is from the beginning of civilization. Empiricism was let's say, the precursor of experiments, right? And the second was theory. Theory started again from the old civilizations, from Mesopotamia, from ancient Egypt, from ancient Greece, and started practically via philosophy, mathematics, and later the theoretical science. That were the two routes for advancing, let's say, science and technology. All these were true till about 1945. So at 1945, there was a revolution, kind of revolution in quotas. Do you have any idea what happened in 1945? It was, of course, the end of the Second World War, but this is not relevant to what we are doing here. It to what we're discussing here? What is relevant to what we are doing here? Huh? Theory. Theory it was even before. Theory of computation was, but it was not exactly 1945, it was a bit years, so let's say before. There were ideas about the theory of computation, but 1945, what happens actually? It was something that we needed, we don't say it all the time, but we need in order to perform what we're doing here, and this is this thing here. Now, if you are, let's say, if you have not seen the history of computers, then you will not be able to realize what is this thing here. It seems like a factory or whatever, but this actually is the first computer in the world. Of nowadays, what is recognized as the first, and this is ENIAC. It had this very complicated name, electronic numerical integrator and computer. So actually, to be fair, there were computer-like machines before that. Nevertheless, ENIAC is considered to be the first, as you see here, programmable electronic general purpose digital computer. So it was the first machine that it was possible to program on it and then to resolve problems on that. So using a kind of programming language. So the idea was that it was Turing complete based on theory. This is not relevant to what we're discussing today, but it's important to understand that this is really a crucial moment because we have now the first machine in order to be able to solve computers on that. So this was ENIAC, and after that there is this very famous Moore's law. It's not a real law; it's more like a semi-empirical observation. According to that, every about 18 months, we have the double the number of transistors per area actually is being increased 2 times every 18 months. So we have this exponential growth, with other words, and this leads to something like that. So here, if you see, again, these plots are, we have time here, and then we have here calculations. So we can easily transform transistors per area in calculations, let's say. It's again, as I said, more like a qualitative graph, but again, it shows us the trend, and the trend that you see resembles this exponential growth. Now, again, to be fair, if you see here, we have some machines going much before 1945. Nevertheless, as I said, these machines were more like machines in order to solve specific problems, and it was not possible to reprogramming that in order to solve general purpose problems. That's why ENIAC is considered to be the first one. Now, this is important because due exactly to this exponential growth, and nowadays there is this huge increase in computational power. So again, the fact that we are here, that we are able to do this research, that we have this center, that the computational sciences and engineering is a so important field throughout the world is exactly because we have the machines to do that. And as I was saying, this exponential growth led to more than 16 orders of magnitude increase in computational power. It's really something amazing here. So there is no any other invention actually with such advancement within only 70 years. It's really something huge. So actually nowadays, even the mobile phones that we have are much more powerful than this ENIAC here. So this shows exactly the level of the computational power. And nowadays we are from this level up to the exascale. Now the strength, just to remind you again, the number of calculations typically is computed as floating operations per second. So these are real, let's say, number calculations per second. And nowadays we have exascale. Exa means 10 to the 18 floating operations per second. So these are really numbers that the human mind cannot really, I think, deal with. But this is exactly the reason. Actually, this is not Frontier, it's El Capitan, and this is is the fastest supercomputer nowadays. But this exactly shows this huge increase in the computational power that allows us to solve problems. And now coming back on that, since we have now the computational infrastructure, the idea is to combine now what we know from theory, what we know from experimental observations, and this is definitely a multidisciplinary field that involves science and engineering, as you see here, mathematics, computing, and the overlap between all of them is this CSE, which is computational science and engineering. Okay, so this is the part of I would say, a new discipline here. If you see now in the core of this discipline, we have the model. The model is how we describe, let's say, the real world. Again, in our discussions and the examples that you are going to see here, we're mostly dealing with materials, but this is just one. Of course, it's not the only part of the real world. In general, if we are able to create a model of any physical system, and we are able to solve this model in a computer, then this is part of what we call computational sciences and computational models. And of course, as I was saying, this is coupled with what we call high performance computing, which are the methods that we use in order to solve these problems. Okay. And this is again the let's say the more general description of this computational science and engineering field. That in the general let's say description here refers to all these HPC techniques that are used in order to solve problems in science or engineering, and in general in order to model natural phenomena. Now, if you remember, I told you about the empiricism and the theory. So these were the two routes for scientific discovery. Now, the computational science and engineering is the third pillar of discovery. And nowadays, of course, this is coupled with what we call data science and machine learning. You are all aware about that. Typically, we describe the machine learning methods, or AI, if you want, technologies nowadays, as the fourth paradigm that was actually named from Microsoft a few years ago, which is called the fourth pillar of scientific discovery. So if you see now, if you think, the human civilization proceeded for several thousands of years via these two routes, empiricism and theory. And after 1945, already in only 70 years, we have already two other now scientific pillars that help us in order to understand the physical phenomena and also to advance our lives. And this is the computational methods and also nowadays data science and machine learning. So practically, of course, computational science and engineering concerns, let's say, both these two pillars, which is the high performance computing and the data science. Okay, and this is the two, as I was saying, very, very advanced fields that nowadays are of extreme importance for several, if not for all, I would say, scientific and technological problems, right? Now, if we go, let's say, from this overall description that refers to computational science and engineering, we are going to focus a bit more on materials, or what we call here molecular systems quite often. And the idea here is that if you think a bit again from history, typically materials, actually we characterize eras, historical periods, by materials. So do you remember this? We have the Bronze Era, we have the Stone Age, the Bronze Age, the Middle Age, before that the Iron, then the Industrial Era. Nowadays we call it quite often Info Age or Silicon Age, silicon because of the computers again. So this shows exactly how important are materials, and we can understand this from our daily lives as well. I mean, I don't need to show many examples here, but if you consider our daily lives, in all cases, we are dealing somehow with important materials that are used for several different applications. And this is, of course, I mean, just, in the automotive industry, as you see here, we have materials that are crucial for all the different applications. And another example here is soft matter. Soft matter practically refers to materials which are characterized by energies which are of the order of kBT. kBT is the thermal energy. So practically, these are materials with this property that are something, let's say, between liquid and solid. And again, this is a very broad family of materials, starting from biological systems, proteins, DNA, colloids, surfactants, polymers, etc. Now, in all cases, the take-home message is the following. In order to address all these important societal challenges that nowadays we're discussing, for example, we're discussing about green transition, about climate change, about new advances in medical sector. Now, so again, the message here is that in all these cases, in order to be able to address such challenges and so important problems, we need to first to understand the behavior, the properties of the materials, and this is the scientific part. But also we need to develop new advanced materials with the desired properties. So this is something that I would like to always remember. This is the technological part. That's why typically we say that materials is a horizontal sector. So there is not really materials only for energy, only for climate. It's a horizontal action, and it really fits with any kind of challenging application or societal challenges, as we could call it nowadays. And this shows, again, the importance. Now, from the computational point of view, the holy grail here is to be able to predict what we call structure-function relationships With other words, to be able to predict the macroscopic properties of the materials, starting from directly from their, if possible, molecular structure, atomic level. So starting from the real, let's call it chemistry or physics, to be able to predict their macroscopic behavior. As you understand, this is an alternative or a complementary technique to all the experimental methods, right? So this is what it's relevant to what we call in silico studies. In silico, again, is because it's in the computer. In silico studies or in silico design of the materials. And just to give you an example, for example, let's consider tire materials. So let's say that you need to develop new tire materials. Here, the first requirement is safety, of course, as we all know. And for that, the properties related to roll resistance are extremely important. At the same time, durability and abrasion resistance, all these are properties for the specific applications. So with other words, what we need here is we need new advanced materials that are able to have the optimal properties across all this sector of different techniques. And this is really very hard, a very difficult scientific and engineering problem, because someone needs to go, again, from the specific chemistry, from the atomic structure, up to the macroscopic behavior and the engineering scale of this thing. Now, this concerns tire materials. Another example, it seems much different, but again, you will see that properties are very close, related to drug carriers, and these are, of course, this is a very extremely important problem in medicine. So again, here, as you see, these are complicated multi-component materials that need to have specific properties. Yes, typically in that case, we have something like a carrier here, and inside the carrier, we have the drug. So the idea is that the drug and the carrier should be compatible, and at the same time, we should be able to guide them in the specific part, let's say, of the human body or whatever, in order to have a target drug delivery. It's again one of the most important problems in medicine. And if you see here, the properties that need to be optimized are related with what we call control release, with the stability here of the nanocarriers. Typically, they are nanoparticles. They should be, of course, biodegradable. Otherwise, it will be non-toxic, of course, non-immunogenic, etc., stable in blood. So these are just a few of the properties that a material needs to have. And that's, again, shows the complexity. So it might be not so hard, let's say, to have one material with one of these properties only, but to find a material that combines all this, if there is such material, this is really a very, very important and difficult task. And this shows exactly the complexity. Due to these complexities, it takes so much time in order to develop advanced material for specific applications. Another general now here example refers to what we call multi-component systems and interfaces. Interfaces are regions where the properties of the material change. So we have a multi-component system, and in between these different components, for example, here we have nanofillers within the polymer matrix. So in between these different components, we have this, what we call interfaces, which are regions with where the materials have different properties. So again, here, what we need is to study these regions here, to study both from the view of physics, of the basic, let's say, scientific part, but also to design new materials with the desired properties. And this is a very, very hard problem. And just here, I like this motto by Wolfgang Pauli, who was an eminent physicist, experimentalist in the field. And he used to say that God made the bulk, surfaces were invented by the devil. Exactly in order to solve the complexity of because he couldn't control as an experimentalist what was happening at the interfaces. So, and this is again a field where computational methods, and I'm sure that you will see examples in the later in the lectures and the hands-on session. It's definitely a field where the computational methods, and especially ab initio quantum mechanical methods, can help. Right. So now again, the message here is that from the computational point of view, these are, let's say, the grand or the major challenges. First is to understand, as I say, to predict these structure property relationships for the materials, to design new materials, of course, and if we go in the specific here level, then to examine, let's say, heterogeneities or properties in the interfaces or in multi-component systems, if possible, starting from the atomic, sometimes subatomic, as we will see, and molecular level. Now, again, by definition, as you understand, the main characteristic in this field is what we call multi or interdisciplinarity. And practically, if you see the scientists, let's say, who are working in the field, they are not at all from a single scientific field. And this exactly because this materials field involves definitely physics, chemistry, engineering, biology, when we're talking about biological systems. And as you see here, all these different of different fields and different expertise. We always say that in the core of that is what we call computational science, this new field that practically combines, let's say, different disciplines here. And of course, mathematics, we need mathematics in order to build the models, right? So it's really a very, very broad and interdisciplinary field, transdisciplinary better. And definitely we need, again, this is a take-home message, we need really expertise from many, many different fields. So it doesn't matter what's your degree, let's say, or what you are studying, but definitely we need the background of that. And just to give you one more example, in order to understand the complexity, let's take a single molecule. This is a single macromolecule. We call them polymers. If you are not familiar with polymers, it's not a problem. It's just to understand practically they are big molecules, let's say, which are connected, and we have repeated here units that they are called monomers bound together. So we have a system where both entropy and enthalpy are important. And typically we assume that they follow random coil, so random walk statistics. Nevertheless, this is not true, of course, for all macromolecules, for all polymers. DNA is also a polymer. And if you remember from DNA, we have this helical structure, which is definitely not a random walk. This is just, again, to show you the complexity. And not only that, but within a single molecule, so a protein is a single macromolecule, right? So within a single molecule, you might have many, many different structures and many, many different length and time scales. So assume now that you have, let's say, a microscope, and you are examining the system from the top, and you go towards the examining in more detail, then you would be able, if you had such an idea, let's say, apparatus, then you would be able to observe something like that in the macroscopic level, and these are from TEM or SEM images, so real experimental images, you will see a kind of structure. When you go now towards the molecular scale, you will observe something like in the semi-macroscopic or mesoscopic, as we call it, scale here. So here you see corresponding length scales. If you are able to see atoms, then you would observe something like that. And if you are even able to see, go below atoms in the subatom regime, then you would be able to observe something like that. Here we have a tetrahedral form of methane, right? So practically there is not any experimental technique or single experimental technique that I can give you, of course, all the structure. There are very many advanced and very expensive, actually, experimental methods that are able to check these levels. Now, but exactly this complexity here shows that there is a very broad range of length scales that characterize these systems. And at the same time, there is also a very broad range of time scales. So assume, for example, that you want to calculate, let's say, bond vibrations in a system. Then typically bond vibrations occur within the range of a few femtoseconds, 10 to the minus 15. Whereas other phenomena, as you see here, occur at a very much longer time scales. The time scales here can be even of the order of 1 second. When we are close to the glass transition temperature, which shows it's a transition between a glassy and the liquid regime. And if we have collective phenomena, these characteristic relaxation times might be even longer, might be even days, years, or even longer. So practically, this means that we have a very broad range of time scales as well that need to be considered if someone is interested to calculate everything, which of course is not practical. And on top of that, there is this famous curse of dimensionality. So again, to remind you that when we are talking for, let's say, quantities in real life, practical material quantities, then typically this, let's say, real life samples, let's call them, involve a very large number of atoms of molecules. That's of the order of Avogadro. Avogadro is 10 to the 23. It's really a huge number of atoms. And not only that, but if we see, for example, a single polymer chain, that is like a protein, which has different types and consists of 100, let's say, repeat units, then the entire potential phase space here of potential chains, different chains that can be made, it's 10 to the 100. So again, these numbers are really intractable. This means, again, that, of course, we are able nowadays, due to these supercomputers, to simulate, let's say, large systems, but again, not at all with these numbers 10 to the 23 in the atomic level. This is, again, why we need now a different technique. So again, this, I would say, is probably the most important take-home message. This is the idea of what we call multi-scale modeling or hierarchical modeling in these systems. So exactly due to the complexities that we have seen so far, there is not a single technique that can describe you the entire phase space or the entire spectrum of these length and time scales. And this is the idea of let's call it multi-scale or better hierarchical modeling across scales. The plan, again, if you are not familiar with such plots, we have typically, these are qualitative plots. There is the time scale here and the length scale. And what we present you here is practically methods that are capable of describing a window of time and length scales. And here, typically, we start from the most detailed level, that is the ab initio simulations. So here we have the quantum level that, as you will see exactly actually in the next lectures and in today in the training events, so you will focus more on density functional theory. So practically today, the training event refers to this time window, okay? But then we have also the atomistic here level. So in this case, we describe the system starting from electrons. So we have nucleus, we have electrons in the system. In the atomistic scale, we forget about electrons and we describe each molecule as a single point. That's the classical, as we call it, description. Again, very detailed, but at the same time, still very consuming. And then there are more, let's say, as we call coarse-grained methods. So methods where we forget now so much the detail, and we try to develop more efficient models, but of course we lose some information. There is no free lunch here. And these are the coarse-grained models as we see here. So instead of atoms here, we describe the system via what we call super particles or superatoms. And then there's the continuum scale. I'm sure that you are all aware about that. Typically, in that case, we forget about the structure, the atomic structure of the system, and we describe the model via continuum equations. For example, Navier-Stokes is a very good example of this, or finite elements where we describe the system in the continuum scale. So this is the main idea behind this multi-scale. And as I was saying, of course, there is not a single technique to describe everything. Practically, this means that we need all these techniques. And the main challenge here is, if able, to build, let's say, quantitative and rigorous approaches in order to bridge the different scales. This is the whole idea behind of what we call bottom-up approaches in this field, right? And now nowadays we have this scheme here. A main challenge in the field is how we obtain methods that link here different levels of description. And these have been, let's say, traditionally achieved via inverse problems methods. Just to remind you, in the inverse problem, I mean, the main idea mathematically is that we have the forward problem. The forward problem is that we start from some, let's say, parameter observations. We build a model, we solve the model, and we predict the properties. This is the classical forward model, like the simulations that we typically observe. The inverse problem is now we start from data, right? So here we start from this now part, measured data. This could be either experimental data. In our case, our data coming from a detailed simulation, and then we create the model and we predict the parameters of the model. So with other words, we try to find the model that best reproduces the data, right? So this is the inverse method, and this actually nowadays can be described also via an optimization problem of this form. So D here are the data, and P is just the parameterization of the model. So capital X here is any parameter that you are thinking, any property or whatever, and theta, which is the most important, is the model parameters. So again, the idea is to use some data, and if you think a bit, this is at the heart actually of all machine learning methods, because we have the data and we try to find the optimal model parameters or the optimal network, if we are talking in the machine learning and neural network language, that reproduces the data. Okay, so as I was saying, this was the main, let's say, description of that. And now for the rest of the presentation, there are some examples, starting mainly from the atomistic scale and above, since in the next lectures and in the hands-on, you are going to observe, you are going to see in much more detail the density functional theory and the ab initio part. Okay, so for the time that I have, let me see, not a lot actually, it's about 10 minutes. I will give you a few examples on that. And please, as I was saying, even after the presentation, don't hesitate to contact us anytime. So again, let's see now that we start from the classical level. In the classical level, don't be afraid about the mathematics here. They have just a few equations, but these are very basic. Actually, here we have the classical equations of motion. So it's the most basic physics that we all know, right? So we have a Hamiltonian, which is a kinetic energy plus the potential energy. From the Hamiltonian, we can define equations of motion, and this is classical equations of motion. Now, the important thing is U here, because in practice, let's say if we neglect quantum phenomena, and if we assume this classical description, these equations of motion can be used in order to describe atoms, but at the same time, they can be used in order to describe planets. They're the same form, practically. From the mathematics point of view, they're exactly the same equations. What is different is this U. So the interaction, practically, which determines the underlying physical system. And now this is when we are at the atomic scale or the molecular, let's say, level, we need actually here a function that is somehow able to accurately, or as accurate as possible, to describe this, the real, let's say, underlying physics and chemistry. Now, as we all know, this is the real, let's say, physics and the real chemistry. It's the result of an underlying many-body quantum problem. So practically, we have here complicated, let's say, functional forms. It's all this type here. I don't need to go in details. That somehow try to approximate this many-body quantum mechanical problem. Again, as you will see later, this, in order to solve accurately this many-body quantum mechanical problem, it's really a very, very expensive technique. So if we want to simulate systems with several thousands of hundreds of thousands or millions of atoms, this is still not yet possible to do it with ab initio methods. That's why we need the classical molecular dynamics or classical molecular simulations, might be Monte Carlo, so algorithms. Again, in order to use these algorithms, at the heart of that is this U, which is exactly the interaction potential. Okay, and the only way to obtain now this the model parameters here, it's again via fitting procedures to either to data that are coming from ab initio calculations, the most detailed level. Again, you should have in your mind this ladder that we build this bridge from the ab initio towards the atomistic scale. Of course, if we have experimental data, accurate experimental data, then we can use this data in order to derive these parameters. And here you see some characteristics of that. Okay, and just to give you an example of how we fit, let's say, this data. Now, this is like spoiling now, because this will be probably in the next presentation. This is the Schrödinger, the many-body Schrödinger equation. But what I would like to show you now, that the main idea is we start from this level here, where somehow we're able to approximate the Schrödinger. This is the ab initio part that you will see later. We have these interaction energies. And then what we do is via advanced optimization problems, we try to find the optimum U of R here, the optimum, let's say, model parameters in the classical scale that reproduces this interaction energy. So it involves, as I was saying, a highly nonlinear and typically complicated optimization problem, but this is the main idea on how to create a quantitative model here, because we need a U of R here that is able to compute and to describe accurately real physical systems. Okay, and this also shows some here characteristics. As you see here, the number of the atoms that can be simulated with in the ab initio scale is of the order of 100 or maybe 1,000 atoms, but it's difficult to be more. With the classical simulations, it can be of the order of several million atoms nowadays, and also time scales of the order of several dozens of microseconds. Okay. And now, in order to do that, as I was saying, we perform DFT calculations, and then we solve this minimization problem. So again, this is the result of what we have seen before. So we have now the DFT data or the ab initio data. As I was saying, if we had very, very accurate experimental data, it would be possible to use them. And then practically what we do is we fit this algorithm. This can be fitted nowadays with machine learning methods. That's why typically we call this machine learning assisted, let's say, potentials or base potentials, because we use these models, these machine learning methods, in order to parameterize the U here. Again, it's a typical optimization problem. We find the best model parameters that reproduces now the ab initio data. Okay, so this creates, let's say, a workflow now for doing this coupling from the DFT from the ab initio to the atomistic level. And if you see this for a polymeric system, so here we have polymer with a substrate. I will not go in details in all the systems. The idea is, again, we perform DFT calculations of a single here molecule, because we can do much more in the ab initio level. We use these machine learning methods, and then we develop here the force field, and from the force field, we create here simulations. This is practically, we solve dynamical, it's a dynamical system mathematically, so we solve equations of motion. This means that we can create these videos. This is straightforward from all these atomistic simulations. And this actually, from the time evolution of all atoms here, we have coordinated velocities for each atom. we are able to calculate the properties of the material. So again, this is the idea. Of course, as I was saying, we're talking about here systems up to, let's say, million or a few millions of atoms if we have access in the supercomputer. These are really very, very demanding still calculations. Nevertheless, they are very detailed. So it's, I mean, experimental, typically, it's impossible to have this information. And again, this is a take-home message. So the simulations of whatever we discussed today, it's important. It's important because, what happens? Because typically it's very difficult to, what happens here? Sorry, it seems that somehow. Can you see the screen online?
Yes.
Okay, great. Somehow decided to. In any case, since I don't have a lot of time, I will pass the rest of the examples rather fast because I gave you already the take-home message. That was what is still important. Now, of course, if you are interested on that, there will be additional training events. There are many workshops also that we are doing from time to time. So again, the important thing here that I would like to stress out is that since these are really very detailed techniques, we are able to calculate properties. And here you see a nanostructure material, polymers and the substrate, and you see the density as we go far away, the density of polymer chains far away from the substrate. These two peaks here that you see is the high dense peaks due to the double chemical bond. This is again something that experimentally it's almost impossible to take it. This is what we expect. The fact that we expect from chemistry, the fact that we're able to see with the model is a justification, actually, that the model is very accurate. If you see here, the ranges are of the order of a few angstroms only, so 0.7 up to 1 nanometer. So really very, very, very small length scales. And from that, we can also calculate other properties like the glass transition. Now, glass transition, if you are not aware of this, it's a very well-known and important macroscopic property that determines practically also the range of applications of materials. So just materials above TG, practically they are more close to fluid phase or viscoelastic phase if they are polymers. Below TG, they are, their behavior is more like a solid. The fact that we are able here to calculate the TG is very important because as you see, the TG at the interface is much different than the interface, the TG in the bulk. So this shows again that the properties of the material, the interfaces are different. Now, we know that, or we expect that from the point of view of physics, but again, experimentally, it's impossible to get, let's say, detail in what is happening within a few angstroms from this interface. That's why these techniques are really unique from this point of view, and you will see many examples also afterwards, because to calculate, for example, electronic properties, as you are going to see, for such length scales is extremely difficult with an experimental technique. It is possible to do it with ab initio methods, as you will see later. Okay, and now this can be continued actually to the next level, so I will pass fast these things. So starting now from the ab initio to the atomistic, then the next, let's say, level in this ladder is from the atomistic scale to the mesoscopic scale. So in this practically, in this example, we have a coupling between this description and in the more coarse graining, as we call it, one. And nowadays, we have also machine learning methods that are capable of going from the one level of description to the other. So from the atomistic to the coarse graining and then backwards, because quite often we need atomic detail or we need atoms in order to calculate properties of interest. And this is an example of how we go back and forth actually in this field. And in that case, this can be done with deep learning models like variational autoencoders. I will not go in detail on that, but if someone is interested, we can contact me. And the last example that I would like to show concerns polymer nanocomposites, another, again, very important family of materials. Here, again, the question is to predict the properties of materials starting from the atomic molecular scale. We know experimentally that when we have a matrix and we add a filler, then the properties of the hybrid material are different. And they cannot be actually described, we cannot describe them with simple, let's say, hybrid or mixing rules, exactly due to the presence of the interfaces that we have seen before. And here is again the density. the density, the polymer density is a function of distance from the surface of a nanofiller. And as you see here, it's highly heterogeneous. That's the message here. So it's not really that we go from 0 as we expect towards the macroscopic, the bulk value, but there is this structure here that shows that the material is not exactly the same as in the bulk region in this interface. And actually, since we have all this information, we can perform also kind of 3D, as we call it, tomography in the pictures and calculate all these properties, calculate macroscopic properties like viscosity and other very important property. And actually here you see predictions coming from different levels of description, as I was saying you before. And at the same time, we have experimental data. There is no any fitting here. And if you see, the agreement is excellent, especially if you consider that experimental data might refer to also uncertainties in the measurements, in the sample, etc. And again, if you see here, there is more than 2 to 3 orders of magnitude cover in the molecular weight here, how long are these polymer chains, and several orders of magnitude in the value of the viscosity. So starting from the less viscous, more like fluid-like behavior, towards the viscoelastic regime. And then this can be extended also to non-equilibrium properties, and this is the mechanical behavior. So we can perform here some kind of deformation. Here we mimic now non-equilibrium conditions. So we perform some deformation. With that, we calculate stress versus strain. And from that, someone can calculate mechanical properties like the Young modulus. And again, the idea is via advanced here optimization techniques. I will also skip this part and give you just the message here. The message is that we are able to calculate what is happening and what are the properties in the different regions of the material. And here we're talking about mechanical behavior. And as you see here, the mechanical behavior of the interface, it's much different than in the matrix. So with other words, the properties of the material are different in the different domains. It's the same material, the same physics, the same chemistry. Nevertheless, because of the interaction between the matrix and the filler, the properties of the material are different. Right? And this can be extended now to the continuum scale. So this is the last part in this ladder from the mesoscopic up to the continuum, where someone can develop new finite element models in order to describe these materials. I think I will stop here. Before stopping, I will give you another example, which is much more popular, I would say, than our work. And this is actually the Nobel Prize in Chemistry last year. It's the AlphaFold, because AlphaFold, again, is doing something like that. Here, actually, AlphaFold considers a single macromolecule only, a single protein. Nevertheless, exactly because of this huge space, is the curse of dimensionality that I told you before, to be able to predict the 3D structure from its amino acid sequence, it was, and I would say partially it still is, a very open and a big problem. So it's not really that the problem has been completely solved. But nevertheless, AlphaFold, it was the first algorithm that were capable of, let's say, having very good predictions, as you see here. In this CASP, it's a very long time, very popular competition in molecular biology, where different algorithms are trying to predict and to solve exactly this problem here. And the AlphaFold was very popular on that. And that was the reason that got the Nobel Prize in Chemistry. Nevertheless, this is a statistics-based algorithm. So accuracy is not really, it's not 100%. So the problem is not really that has been solved completely. And I would say also does not reveal the mechanisms of the protein folding. So take home message. The computational, I would say, start with the more, let's say, we should be modest in this field, because the systems are really very complicated. And I would say that whatever we do at the final end, if we are dealing with macroscopic problems, macroscopic numbers, the curse of dimensionality, it's always there. So we cannot really avoid that. But being able to couple these different levels of description, the different models, the different algorithms, the good thing and the good news is that we are able to describe quantitatively nowadays a very broad range here of length and time scales, and also molecular weights if we consider polymers, and help us to this combination of methods and of different expertise from many disciplines allow us to provide a fundamental understanding of this, and this is the scientific part, and also from the engineering point of view to help us to rationally design new materials. This is the technological, let's say, part of that. So really main conditions for that is that we need, beside the machines, we need infrastructure, computational infrastructure. Here we are lucky because, let's say, we are a computational Center, we have National Supercomputing Center, but nevertheless, we need access to large scale computers. At the same time, we need new models, even better models. So we need always to try to derive accurate models, if possible also to provide uncertainty quantification here, a new algorithms for treating large data sets. This is the part of the database. So I will close with a question that I've started with a philosophical, let's say, question. So the question here is if it is possible to develop a perfect model algorithm for any kind of physical system. What do you think? Is it possible or not? No. What about the rest? Nobody is more optimistic. Maybe for Zoom. What do you believe? Someone from online people. Do you think that it might be possible? I didn't say when. I mean, it might be possible to develop this algorithm after 1,000 years. The question is more philosophical. Is it possible to develop or not? Yeah, it might be not the algorithm of everything, but of almost, let's say, everything. Let's say even for a specific physical system, but to describe perfectly this system. Okay. So actually, as I said, in my view, this is a philosophical question, which means that we don't have a definite answer. That's one of the differences between philosophy and science. So in philosophy, you can never have definite answers. So this means that you can have different here views to see this. I would say that there is the engineering approach, how to answer and how to deal with this question. The engineering approach is actually like this motto by George Box, who was saying that all models are wrong, but some are useful. This is nice. I like typically to paraphrase that a bit. I think all models are correct, but are correct given their specific assumptions. So if we assume something about a real system, then the model is correct. If you see the mathematics, this construction of the model, and we start from some assumptions, the model is correct. But of course, some of them are useful, let's say, for describing the real system because the specific assumptions cannot describe exactly the real system. As I was saying, this is an engineering approach, very practical. Now, there is more like before closing that, of course, if we believe this approach, then the absolute test is always the reality, right? So whatever we do here is perfect, but we need to have good experimental data, good accurate experimental data for good systems. So this means that models and experiments that go always together. We cannot really avoid experiments in order to construct the perfect model or the good model. This is, as I was saying, the engineering approach. But if you think a bit Plato again, if you remember, Plato was saying that there is another world, which is more real than the physical world. So if you remember this theory of forms, then we have the mathematical approach. Let's call it all the philosophical. You can name it. According to that, this world, the world of model, let's call it now, it's more real than the real world, right? So this means that we don't care so much about the real world because the models can be even more real than the physical world. Okay. So this is, I would say, more or less optimistic from the point of view of algorithms point of view and model. Nevertheless, whatever you believe here and whatever you follow, I would say that, again, the last take-home message, it's really a fantastic time to be involved in the field. This field has been started only 70 years ago. 70 years is nothing for the advance of human beings. But again, the advancement in these 70 years is really enormous. Actually, nowadays, with these exascale machines, it's really, I mean, here sometimes people were confused because we cannot understand here the numbers. I mean, exascale, it's not important only because we do more calculations. The main idea is exactly because we are able to do these calculations, to use much larger model, we are able to do more things. We are able to develop new advances and to address challenges that was not possible to be addressed even a few years before, not decades. And also this is going, of course, together nowadays with this with the exploration of large data sets. So classical, we call it computational methods together with data analytics and machine learning algorithms are going together, and we are able with that, and that's the goal, of course. That's what we are doing. Whatever we do is to address important, let's say, societal challenges and problems that would be impossible to do a few years ago. And I will close you with just to show you from the computational infrastructure point of view, all these are new advances during the last 3, 4, 5 years. So these were the pre-scale machines. I focus only in Europe here. And all these are practically via EuroCC and the Partnership for Advanced Computing, the PRACE. It's a big organization that we are part of this. These were the petascale machines. already several of them. There were 3 or 4 pre-exascale, and nowadays there are the exascale machines. 2 of them actually in the USA, at least 2. This El Capitan is the fastest nowadays. In China, we don't have a lot of data, but there are definitely some of them. And a few months ago, we had also the first exascale machine in Europe, which is in Jülich. There will be a new one in France. Actually, all these machines are available to everyone. That's another very important thing. So everyone from any part of Europe, for the European machines, can send an application. There are calls. These are competitive calls. Write an application, write a proposal for a specific scientific or technological problem, and he or she can use these machines. I will close. I have to, okay, here acknowledge several people in the group. I will not mention names, but all this is just, of course, is the work of many people, and thank you very much for your attention. So we start some minutes later. There is no chair. Yeah, no, I chair myself initially, no problem. But I was saying that I started a bit later. But I think, yeah, if you have some questions, of course, there will be now the next presentations where we'll be more focused on the ab initio methods, and then the hands-on session, which is the most important part of any training event. But please, if you have any general question, any comment, also the online people, please don't be hesitant. The online people? Please, Maria. Yeah, you can start. Yeah. I'm not sure if they can hear you, Maria. Spiro, do we have that? No, can we use one of them or not? Because we have so many.
Hello, Vangelis. Thank you for the nice presentation. So one very generic question. So yeah, you mentioned just right before that we are entering the exascale era. Do you think applications in when you show AlphaFold and all this kind of stuff, do you think that we are really entering in an era of materials design where computational approaches, even on atomistic level, they will really change the world?
Yeah. So thank you very much, Mario. This, of course, a very, very, very general, very important question. This is exactly the goal. That's what we are doing, whatever we do here. So there are already sectors, technological sectors, who are taking advantage of that, even if they're in their everyday, let's say, work. For example, the drug sector now, every R&D department has several computational sciences who are working, many of them from ab initio level, definitely the molecular level, in order to try to screen out potential candidates for new drugs. So this is true now that is happening also in the all advanced, let's say, big companies in materials. So that's generally, definitely this is the goal and this is the idea. Now, of course, it will need some time, let's say, this still to be part of all companies, and we need some time for the mature of the algorithms, but definitely this is the scope. And I think what is important, at least I have seen now as I'm becoming older, let's say, I've seen a big transition towards the times I comparing with the time when I was a student. So now when we discuss with companies, many big companies especially, they have already understood that they know how important is this thing. At that time, it was before 20 or 30 years, it was much more difficult to convince them that you need to invest on this. Nowadays, and as I was saying, drug sector, it's something that it's mature already for a few decades. But now this is true also for other sectors like entire materials, like automotive industry, like electronics for sure. Again, the idea is more like the engineer and here approach. It's not that we will completely forget experiments, we will do computational methods and simulations. This is not the scope. The idea is that you will be able to use as a complementary technique. It's much more, it's less expensive as the very advanced experimental methods. That's another important thing. And with these methods, we will be able, from the point of view of in the industry, we'll be able to screen out potential materials for desired applications. I think that's the more pragmatic approach. Instead of, let's say, doing 1,000 different synthetic experiments, which can be very costly, to synthesize 1,000 new drugs, for example, or new materials, we will be able first to to do the simulations, to do the screening here, and to find, let's say, 10 candidates. And then we're going to use these 10 candidates in real practice now, in experiments, in order to find the best material for the desired application. Again, as there is not the perfect model, of course, there is not the perfect material as well for all applications. So this is exactly the complexity of that. Sorry. It seems that this one. Battery decided to do anything. Okay. Oh. Sorry for that. Anyway, I think we were, Maria, I think it's good because we're a bit late. Okay. So now we will proceed. Since there is no chair, I will chair the next speaker. So, Maria. Yeah. Okay.
I will.
Use this.
A second. Let me knock the audio and I'll video and I'll give you anything. Thank you, Angel.
Okay. So just as a last remark, as I was saying, if you have any question in the comment, please don't hesitate to contact us, all of us. And it's my great pleasure to introduce Professor Mario Zacharia, who's the new faculty in our center. Mario is an expert in the ab initio methods. So this presentation will be more now focused on how we use ab initio calculations in order to predict properties of material.
Hello? Can you hear? If I talk from here, it's okay. They can hear me. I don't, and I have my audio off on Zoom. Okay. Got it. Let me one. Okay. So hello everybody. Let me first go through the website. So I guess you'll have the link for the website. And here basically you'll find where is the training material? Training event material, sorry Spiros, here it is. So if you go in this link here and you like type the training event material, basically here you'll find all the like presentations that I have uploaded. And on the last like line here, you'll find the tarball, which is meant for the tutorial. I'll talk about it later. So today we're gonna talk about first the basics of the electronic structure theory for solids and how we can use DFT. So it will be more mathematically oriented, and I apologize about that, but I wanted to provide. I'm not sharing my screen. Okay, yeah. Oh. Good point. Okay, yeah. So if you go to the the website of the event, you'll find this training event material like link. You press on it, and then you'll see all the files uploaded, the PDF files uploaded for this training session. So in the first one, you'll see like the lecture, the PDF lecture, so you can download it and follow like the lecture, the today's lecture. Will be mostly mathematically oriented, but with very generic equations, just to like show you the principles of density functional theory and the historical development of density functional theory. And then I will talk about the basics of quantum espresso, about the structure of the input files and what outputs we could expect, and some basics input files for basic calculations like electronic structure, electronic band structure, or density of states. And at the end of this training event, we'll have the hands-on session will be very relaxed. And, you know, if you have any questions, you feel free to stop me and ask these questions, okay? So let's go now to the very first part of this training about DFT. Okay. So yeah, I'm Mario Zacharias. As Vangelis said, I'm an assistant professor here at the Cyprus Institute. I started in June of 2025. And it is my great pleasure to be here and like giving, let's say, my first training session on the basics of electronic structure theory for solids and how we can use it through density functional theory to perform like first principles or ab initio calculations. So here is a presentation. This. Yeah, okay. That's clever. Like this. Okay, yeah, that's even better for me. Thank you, Spiros. So yeah, this is a short presentation summary of what I'm going to talk today. So so it's a brief introduction about density functional theory, then I'll talk about the historical development of density functional theory and the main approximations involved. So as Vangelis said, we always start from something exact. So in principle, there is a model, an equation that is exact, but we cannot really solve it. And we start introducing approximations until we make the problem computationally tractable. And then we just, the exact equation is the many-body Schrodinger equation for like materials, let's say. Then we talk about the approximations leading to density functional theory. And finally, we can build on this approximation of density functional theory and go beyond to make our calculations more accurate. So what we do is computational materials modeling from first principles. So by materials modeling is the use of mathematical models to describe materials properties. And by first principles, we refer to a bottom-up strategy. So we don't rely on any external parameters, which is empirical free and relies on quantum mechanics. And by computational, we mean that we require high performance computing and highly parallel codes for solving the Schrodinger equation. So here with this like computational materials modeling from first principles, we can study molecules, we can study simple crystals or more complex structures, or even interfaces and heterostructures. And as Vangelis said in his presentation, the most involved and most complex case is when you study surfaces. Imagine that when you have an interface of heterostructures and you want to examine what's happening on these surfaces here. So density functional theory. In density functional theory, we try to make a computational problem tractable in the sense that we solve a problem of interacting electrons inside the solid. We try to make it a problem of non-interacting electrons, and we try to solve it variationally using iterations until we get convergence in the charge density. I'll talk about this loop later in detail. So what's the progress of DFT and what's the impact of DFT in our community? So here I just went on Google Scholar and I just typed density functional theory and I just copy and paste the results for each year I found, okay? And I just typed density functional theory. I didn't use electronic structure theory. I didn't use ab initio. I didn't use first principles approaches. And as you can see is that the publications, the number of the results are growing tremendously. And here we are reaching basically a plateau around 2029 and 2021. And beyond 2023, I don't include any data because the data are not really updated for 2024 and 2025. And also the reason we see a plateau is because the term density functional theory starts becoming obsolete. People are still using it, but there are more fancy ways to describe these ab initio or first principles methodologies. But the main message here is that the community and density functional theory is making a tremendous impact in our today's lives, okay? And there are a lot of people that they use this tool to make materials predictions. So there are several codes in the literature. So this number of publications that you see here, that they grow with the years, they go along with new codes coming out like every 2 or 3 years. And here I just list a few of the most well-known codes. And we can divide those codes based on the on how they describe the wave function of the electrons inside the solid. So one can use as a basis set plane waves. So here I list the most famous codes first: VASP, Quantum Espresso, Abinit, CASTEP, G-Power, CP2K. And as you can see, some of these codes are either commercial or open source. By open source, it means that you can download the code, you can engineer the code, and you can use it as you want. While if you use a commercial code, you need probably to pay. And if it's for academic use, they usually give you some discount, but you can actually use this code for doing materials properties using density functional theory, all right? So there are other codes that they express the wave functions as a Gaussian basis, and these codes are mostly used for quantum chemists. Here I list a few codes here: Gaussian, Orkan, Cohen, Crystal. And other codes, they use localized numerical orbitals like FHIM, CESTA, or OneTep, OpenMX. And there are some other codes. So all these codes, they start from density functional theory, and they specialize on ground state properties, and they go to excited state properties. And then I also list a few other codes which are very specialized for excited state properties, like exciting and Win2K. So examples where DFT calculations are making an impact. So as Vangelis discussed before, like we are actually entering the high throughput era and the machine learning era, the data-driven era. And here what people did, they trained machine learning force fields based on DFT calculations to make predictions for large protein folding and understand the properties of the proteins. And this might have like a tremendous impact in biomedical applications, okay? So here they used like up to proteins with 10,000 atoms to do these calculations, and they trained their data based on DFT, and then they went to a larger scale using the machine learning force fields to make predictions. So other applications, here I just show a very typical application where we can study CO2 absorption on the surface of cerium dioxide. So people, they used basically DFT to understand how this CO2 adsorbates on the surface of cerium dioxide. And here we see can have a linear CO2 molecule, a bidentate, or like a monodentate. So you can see that here they study in this work the mechanisms that these molecules are adsorbed on the surface of the material. And here I just include this equation. How they did it, they just calculate the binding energy, and they try to find which is the most stable binding energy and most stable configuration, how it absorbs on the material surface. And to do that, firstly, you compute the total energy of the whole system. Imagine that you have CO2 molecules adsorbed on the bulk, on the surface of the material, and then you calculate the total energy with DFT, and then you subtract the individual contributions, which is the total energy of the slab, plus the total energy of the isolated molecule, CO2 molecule, and then here types for the number of the molecules. So in this way, you can find the binding energy and which configuration is more stable, and understand how these molecules are adsorbed on the surfaces of the materials. And why this is important? Because basically we are moving, to the clean energy era, and we actually want to store CO2 and absorb CO2 from the atmosphere, okay? So other applications is to DFT for next generation electrodes in lithium-ion batteries. So here, what they use DFT to support experimental data for applications in lithium-ion batteries using these systems, lithium-based systems. And here you see that with DFT, they can make accurate predictions of the neutron diffraction data, all right? And support that these materials are stable for applications in lithium-ion batteries. Other application, which I like to show a lot in my presentations. So silicon, the most widely used material for photovoltaic applications, there are some mechanisms that allow silicon to absorb sunlight and convert it into electricity. And one of these mechanisms is that when the electron, so here is a typical electronic structure. So here below zero, we have all the electrons lying in the valence band. And here is the conduction band. Is when an electron makes a transition, it allows to conduct current, okay, inside the conduction band. So an electron lying here will absorb a photon and make a direct transition in the conduction band, okay? But this energy is of the order of 3.5 electron volts. So the sunlight is between 1.1 electron volt and 3.3 electron volt, all right? Silicon is an indirect gap material, meaning that the energy from the valence band to the conduction band doesn't lie on the same point in the reciprocal space, which I'll talk later, okay? So here, the electron needs to interact with the phonon and make an indirect transition. And this will give you the absorption coefficient of silicon. And this is how silicon, the most widely used material for photovoltaics, as I said before, can absorb sunlight in the visible region, all right? And here is the agreement between theory, density functional theory calculations, and beyond, for including the effect of electrophonocoupling, with experiment. And you see that the agreement is astonishing, okay? So DFT history. So back in 1920s, let's say, we had the quantum mechanical formulation of the theories that we actually still rely on, and we try to approximate, okay? So that was the quantum mechanical description, let's say, of materials, and where the Schrödinger equation and Dirac relativistic effects, if you want, were introduced in our field. And then it was the Born-Oppenheimer approximation. Of course, most of you saw the movie of Oppenheimer, so it's the same Oppenheimer in the movie here. So if you see in the movie, he actually, Born was one of his supervisors, and they introduced an approximation that is very helpful for us in DFT, which I'll talk later. Sorry. Then I will talk about the Hartree method, which is a mean field approximation for approximating the Coulomb field inside a solid or a molecule, if you want. The Hartree-Fock method for exchange to introduce the antisymmetry in the wave function and respect the Pauli exclusion principle for non-interacting particles. Then the two main discoveries, let's say by Hohen and Kohn-Sham equations that are the basis of density functional theory. They came back in 64 and 65. And then the main problem of DFT since then is how to treat the extension correlation, okay? Which I will talk later. And here they introduce different functionals, LDA, GGA. We can also go beyond DFT and use the Hedin's GW approximation, which is a many-body perturbative approach for the electron self-energy to include quasi-particle corrections. The LEAP functional, and the first application of GW in actual solids came by Hibberstein and Louis in 1986. Then is Bonnepine's random phase approximation. All these are like improvements beyond DFT to make more accurate calculations. Then it's also time-dependent density functional theory. Another approximation, which is very helpful and very computationally manageable, is DFT plus U. I won't talk about this today. Also hybrid functionals, which introduce like an approximation of how to include exact exchange in our calculations. And finally is meta GGA. And now, as Vangelis mentioned, we are entering the high throughput and automated DFT era, where we are producing, using DFT codes, we are producing data like an enormous amount of data, especially with the new developments in infrastructure, exascale computing, and also machine learning functionals. So we left from LDA, GGA, and now we are trying slowly to enter an era of machine learning functionals to treat the extension correlation, okay? So, as I said before, I will talk I'll have some equations, but I won't poison you with all the details. I'll just go so if someone wants to study DFT, he can use or she can use this presentation as a guide to where to look, okay? And what are the main steps? So here is the many-body Schrödinger equation. So we have the Hamiltonian and a wave function that depends on all the electronic positions, which are shown by R small, and R capital is for the nuclei positions, all right? And we want to solve this Hamiltonian and find the total energy of the system, okay? So this wave function, this big object, is an eigen vector of the Hamiltonian, and in total, the energy of the system is the eigenvalue, okay? So this many-body Schrodinger equation has two terms, the kinetic energy terms, one for the electrons and one for the nuclei. Then we have three terms. One is the electron-nucleus attraction, the electron-electron repulsion, and the nucleus-nucleus repulsion, okay? And the signs come basically from the type of forces, if you want, and the effect they have on the total energy on the system, right? So ME is for the electron mass, M capital, so all capital quantities are referring to nuclei. E0 is the vacuum permittivity, and Zi is the nucleus charge, okay? So the Born-Oppenheimer approximation. What these people said, they said just, okay, we know that the nuclei are much heavier than the electrons. So if we assume that the nuclei move much slower than the electrons, we can assume that the electrons follow this nuclei movement adiabatically. So at every instant where the nuclei are, the electron has like a lot of time to adapt on this nuclear motion. So the nuclear motion doesn't really affect the electrons, okay? Only the positions of the nuclei affect the electrons. So in this way, they said, using this adiabatic approximation, I can separate the wave functions for the nuclei, which I present here with X, and the wave functions of the electrons, represented here by Psi. And here we see that the wave function of the electrons, they still depend parametrically on the nuclei positions R, but we can safely ignore the kinetic energy of the nuclei and also the ion-ion interactions, okay? And this we can solve them separately, essentially, or classically if you want, or quantum mechanically, but in a separate Schrodinger equation for the nuclear motion, okay? So here we are left basically to determine Psi. So we can get rid of the nuclei part, and here we want to calculate the total energy of the electrons with the nuclei at a specific nuclear configuration R, okay? And this is called the total adiabatic energy surface or the potential energy surface of the system. So here, Psi still depends on 3n spatial coordinates plus spin, and it's exponentially hard as the number of electrons are increasing inside the system. So it's very computationally difficult to solve the Schrodinger equation. So here I just showed the example of hydrogen. The good thing with hydrogen, there is only one electron, so we don't need the electron-electron repulsion term, which is basically this term is like very involved to compute and also includes some electronic correlations. So if we get rid of this term, and also here, I would like to point out that all the maths are becoming much simpler if we assume Hartree units. I'm sure that everybody in the audience here or in the online audience, you've been struggled sometimes with conversion of units. My thing, it was like a conversion of units was the worst thing I could deal in my whole career. So what we use here in DFT codes and Quantum Espresso, if you want, is that we use the Hartree units and we put the reduced max, the reduced Planck constant, the mass of the electron, and this 4 pi epsilon naught, the dielectric permittivity, and the Borg radius equal to 1. Okay, so this simplifies. So basically, this get rid of all these simples that we have next to the Schrodinger equation, if you see here. And then for the hydrogen atom, because we have only one electron and one nucleus, we need to solve this equation. And this we can do that analytically. So this is a standard model that you learn if you did physics or chemistry, in the first year of undergrad, quantum mechanics course. And here we just find all the hydrogenic levels and the analytical orbitals for the electron wave functions. But already, if we have a system with 2 electrons, it's impossible to do it analytically because we have the electron-electron term, which couples the coordinates. So there is no closed form solution. And we cannot really separate the electron wave functions into a product of individual wave functions. So if we have a system with 2 electrons, we cannot really write it as a product of 2 unique electron wave functions. So the electrons are really correlated, and the motion of the one depends on the motion of the other. So we need to introduce approximate methods to treat this correlation and this exchange. And those are the Hartree-Fock method, or even post-Hartree-Fock methods, configurational methodologies, or density functional theory. Okay, so in the independent particle picture, here I used an example of 3 electrons, of a system with 3 electrons. We can expand the wave function into a product of 3 wave functions. And what we are trying to understand is the electron density at a particular point in space, R. So that means the probability of finding the electron at R1, of electron R1 at position R, the electron that we represent with R2 at position R, or the electron that we represent with R3 at position R. So this probability is given by this integral, by integrating the wave function of each electron separately. And because electrons are indistinguishable particles, we can just factor out this and make it 3 times the first term, okay? But we want to respect the Pauli exclusion principle. In the Pauli exclusion principle, we want that the total wave function is antisymmetric under exchange of any 2 electrons, because any 2 electrons cannot share exactly the same state. They cannot have exactly the same quantum numbers, all right? So we need to account for this antisymmetry of the wave function. And to do that, we need to have the 3 electron ladder determinant. No, here is the 3 electron ladder determinant. If you have a system with n electrons, you need to have an n electron ladder determinant. And this is a very simple object. Don't be afraid, because it's a matrix, or it's a very simple object that you just, try to expand like in the standard way. And finally, you get this. So here, because we have 3 electrons, we do 3 factorial, so we have 6 terms, and we use this as a normalization factor, okay? And here the sign alternates with the parity of the permutation. And if we exchange any 2 electrons, this wave function will become C minus Psi, okay? By exchanging 2 electrons. And finally, if 2 electrons, they have the same state, so if you go back to the matrix and exchange 2 electrons so that they have the same state, you'll have 2 equal columns, and that will give you to 0. So the Pauli exclusion principle is respected using Slater determinant. And why I'm saying all this? Because this is what Hartree and Fock, they use to treat the exchange. They account for a system of an independent particles, okay? So they actually did this expansion because this is the only way to compute the many-body Schrodinger equation, okay? So they wanted to stick with this approximation, and they try to build on that to account for exchange, and they use the Slater determinant. So, okay, now the Hartree mean field approximation. So to ignore, before we said we can also ignore if we want the Coulomb repulsion, but this is a too drastic approximation and it doesn't work. If we ignore the Coulomb interaction, our calculations will be non-realistic, okay? So we need to introduce a mean field idea, and this was introduced by Hartree. So what he said is that I replace this very complex object with an integral over the density, and this is basically the mean field approximation, okay? And finally, and this approximation actually allows us to work in the single particle picture, okay? So we have these 2 equations, non-linear equations if you want, and basically for solving those, we need to do that iteratively. We need to update the electron density, and then, first we need to compute, with an initial guess of the electron density, we need to compute the Hartree potential, then compute these terms and build the Hamiltonian, diagonalize, and find the new wave functions, and compute the new electron density. And then we repeat that procedure until we obtain convergence, okay? And finally, we need to add, not finally, this is the second last step. we need to add the exchange term. As we said before, this can be done using the Hartree method or Hartree-Fock method, okay? And still, this is a mean field because it's one body picture. And this is what we want. We want to keep the one electron picture. We don't want to have like wave functions that cannot be splitted, a total wave function that cannot be splitted into a product of single electron wave functions, okay? And this exchange is a purely quantum correction. But the problem is that if we account only for this exchange, we are excluding the correlation part. The correlation means that the movement of one electron affects the movement of the other electron. And we need to account for this extra term, the correlation term. So without this correlation term, still our approximations are too drastic and we cannot have realistic results, okay? So we can also use some methods like Hartree-Fock, these methods MP2 or CI, they were introduced for accounting for these correlated wave functions, but are computationally very difficult to apply. So we need to resort to density functional theory, which is our today's focus, okay? So in 1964, Hohenberg and Kohn, they said two theorems. So the external potential, the interaction between the electrons and the nuclei, is uniquely determined by the electron density. And the second theorem is that the ground state electron density minimizes the ground state energy of the system, this potential energy surface that we talked before. And this has been proven basically variationally, okay? And here what they said is basically, okay, we add the external potential, we add the Coulomb interaction, like approximated with the mean field theory by Hartree. So we have here a double integral because it's the energy. And we add a term which accounts for the kinetic energy of the electrons and the exchange correlation. And these two terms, they actually contain all correlation effects. And Kohn-Sham, in 1965, they tried to map the interacting problem into non-interacting electrons in an effective potential, so the density, the electron density is reproduced. And what they said, they replaced the kinetic energy of the interacting electrons with a diagonal like object, the kinetic energy of non-interacting electrons, Kohn-Sham. And they said, we put everything else inside this exchange correlation functional, which we don't really know what is that, okay? So we need to account to find our main problem is to treat this term here. And basically, the Kohn-Sham equations, the energy, the Kohn-Sham energy is this kinetic energy term, the external potential, the mean field approximation for the Coulomb interaction, and the exchange correlation energy. And finally, they said that we solve this system iteratively until we obtain convergence, and that based on the final density, like charge density, we can do predictions of material properties or total energies or like bonds, structural properties, and we'll see later that we can also do forces, okay? So the complexity here reduces from a wave function with 3n dimensionality to a density in 3D. So the electron density is just a 3D object, okay? So this reduces the problem a lot. So we just rely on the electron density. And the accuracy, as I said before, is controlled by this exchange correlation term. So here is what we do. First, the DFT code will make an initial guess, and usually this initial guess will depend on the charge density of each atom individually. So we consider a solid, and then we take each atom individually, the charge density, which is simpler to find, and we start with this initial guess based on the position of the atoms, and then we compute the Kohn-Sham potential, then we solve with iteratively the Hamiltonian, and then we compute the charge density. And we are looking for self-consistency in the charge density. So if the charge density at each iteration doesn't change much, it means that we are converged. And this actually gives us the end of a DFT calculation and give us correct total energies, if you want, for a system and other properties. So treatments to exchange correlation again, I will poison you. Most of these are just for you to know that those approximations, they do exist. So one is the very first approximation to the local density approximation. What they did here, they find an analytic for the exchange correlation based on the Hartree-Fock exchange for the homogeneous electron gas. So HEC here stands for the homogeneous electron gas. Then they use the, I think it would be wiser to use this. Anyway. So then for the LDA, they use, like for the correlation part, you cannot really find an analytic expression. So they did it non-analytic from quantum Monte Carlo simulations of the homogeneous electron gas. And this is a seminal paper by Kepperly and Elder. And those people, they essentially introduced the way to treat correlation effects in the local density approximation and beyond. And then is the generalized gradient approximation, the so-called GGA, which is semi-local. And this is because it becomes semi-local because we account for the gradient, not only on the charge density, but also the exchange correlation functional depends also on the gradient of the charge density and becomes semi-local because the gradient accounts for some semi-local regions, the gradient, how the charge density is varying with position. And then for this, we have different flavors like PBE or B88. So one can find in the literature various exchange correlation functionals. And then is the hybrid functional, which is semi-non-local, because we want to include some accuracy in the way we treat exchange. And we do that with the Hartree-Fock, but still, you have a system of non-interacting electrons, okay? So that's why we need to account for this parameter alpha, the screening parameter. So if this parameter is 1, we are going back to the assumption of that electrons are not correlated. So we try to do a mixing of the exact exchange with the density functional theory functional like GGA or LDA. And then is the GW, a way much more accurate way to do many body perturbation theory to account for quasi-particle corrections in the electron energy. And this methodology basically is the king nowadays, although a bit expensive, is the king for computing electronic structural properties. But this methodology, the GW, they still relies on wave functions from density functional theory, okay? So now, we need to go to the reciprocal space, okay? So if we do go to the reciprocal space, so like DFT codes like VASP and quantum espresso, they become numerically more efficient. And thanks to the Bloch theorem is that we can express this wave function into a periodic part and an exponential factor, depending on the wave vector of the wave function. And this is important because all the properties of the solid can be computed within a single Brillouin zone. So any K point that is translationally invariant with any other K point has unique properties. But outside the Brillouin zone, we can always find a K point inside the Brillouin zone that gives the same properties. Okay, so what we have is to integrate, is basically to integrate any property that we want for the accuracy over a K grid, okay, or to integrate over an infinite number of K points that belong in the first Brillouin zone. And finally, we discretize that. Another benefit is that we can use Fourier transform. So we go from the real space to the reciprocal space using Fourier transform. And then we can expand our wave functions as basis functions of plane waves, okay? And this is the plane wave coefficient, and this exponential factor e to ik plus g dot product r is the so-called plane wave. G is a reciprocal lattice vector, and k is the wave vector of the wave function. And r is a point in real space. And this is how we go from real space to reciprocal space using a Fourier transform. So actually, in real space, we have a system with many unit cells, and then we want to do Fourier and go to the reciprocal space and study all the properties in the first Brillouin zone. So this is the reciprocal lattice. So if you did some basic solid-state physics courses, you know what is a reciprocal lattice. And here we take the dot product, B is for the reciprocal lattice, and A is for the real space lattice. And they should be orthogonal times 2 pi. And any periodic quantity can be expanded with this Fourier series. And as I said before, we need to do an integral over the Brillouin zone. And here the n index stands, let's say, for the band index, okay, for the energies. So this is the total energy in a band, and it's divided by the volume of the Brillouin zone. You need to do this normalization factor when you are integrating. And here we have the integration over the Brillouin zone over all k points. And here F is just a Fermi occupation factor that we usually use for the electron energies. And this integral, because really we cannot do an infinite number of k points, we need to discretize and write this integral as a summation over k and divide it by the number of k points for normalization. Okay? So now, what we want to do is basically to make this integration and this discretization. And here we use a uniform grid. So all these dots here, these black dots, they correspond to different k points inside the Brillouin zone. And gamma x and m are high symmetry points. By high symmetry points, we mean that if we rotate these high symmetry points by an operation of the lattice, they will go back to themselves. So gamma point, for example, if you rotate it, gamma point is basically the 0, 0, 0 coordinate. If you rotate it by any symmetry operation of the lattice, it will go back to itself, obviously. Okay? And we use finite k measures for better convergence, and we'll see how to do that also in the hands-on session. And we want to compute total energies and forces. We'll see in the next slide, band structures, density of states, or even optical spectra. And one point that I would like to mention is that as we are increasing the supercell size, we need less and less k points for convergence, because the bigger the simulation cell, the bigger the real space that we are exploring, the smaller the reciprocal space. So we just need only a single point, if we go to a big enough supercell, to sample the Brillouin zone of the supercell. So Hellman-Feynman theorem. Just what we can do, what I want to say here is that we can really do forces with DFT. We can compute forces. And what they do is that they use this Hellman-Feynman theorem. Basically, with this theorem, the forces is the derivative of the potential energy surface, if you want, with respect to the nuclei positions. And you do this simple derivative, and you end up that this term cancels out. Okay? So you are left with this. So this is a very important result for DFT. So DFT relies on this Hellman-Feynman theorem for taking the derivative of the Hamiltonian with respect to the nuclear positions. So here we also add the ion-ion classical Coulomb repulsion term that we see at the beginning of the lecture. And only these two terms survive, because only these two terms, they do actually depend on the nuclei positions. So this, in the Kohn-Sham Hamiltonian, this term, and this term are purely electronic contributions. And finally, we end up with this equation for the forces. And this is easy for DFT to compute. As long as you have the charge density, then you can compute this term easily. And if you are using a linear combination of atomic orbitals and not Poulet waves, you have to add also a Poulet correction. I just add this information here in case you are not using a plane wave code. So if something comes out in the output Poulet correction, that means you are not using a plane wave code. So, and remarkably, the exchange correlation, although it does not enter the forces, they still depend on the exchange correlation functional, because the charge density does, okay? So this is how the exchange correlation enters also the forces. So if you compute the forces in DFT using the PBE functional, or you go to an HSC hybrid approach, you'll expect some differences in the forces. It might be big, it might be smaller. So here I just show like a lattice in real space with like 9 unit cells, and we assume that we have only one atom. So we want to do an expansion of the potential energy surface with respect to the atomic positions. And here actually this is a Taylor expansion, but for many atoms, so don't be afraid with this term. And the linear term that comes after this equilibrium Kohn-Sham energy, with the system at equilibrium, is the linear derivative of the potential energy surface with respect to atomic positions. But this linear derivative is 0 because the system is a static equilibrium, so either lies in a maximum or a minimum. So this derivative reduces to 0. Okay, so the forces acting on each atom at equilibrium are 0. So this is the so-called harmonic approximation. And why this is useful is because when you use the harmonic approximation, you can actually compute the phonons of the system from first principles. So what we do usually in the DFT approaches, we have a big unit set or a supercell. And what we do is that we displace the atoms inside the unit cell, and we try by finite differences to compute the forces acting on each atom. And we put that in a big matrix called the interatomic force constant matrix. And we try to diagonalize this guy here to obtain basically the eigenvalues and the eigenvectors of this system. And the eigenvalues and the eigenvectors of this like matrix here are called the phonons and the phonon eigenvectors. The phonon eigenvectors, they show the direction of vibrations of the atoms inside the molecule, and the frequency is the frequency of vibration, okay? But still, we can get advantage of the reciprocal space. So if we take a Fourier transform of this interatomic force constant and we build a dynamical matrix, so we do this operation here, we have a smaller object for the dynamical matrix at every Q point, at every phonon wave vector Q, and we diagonalize this smaller matrix, okay? And we get the phonon frequencies at every Q wave vector, and at every Q wave vector, and at every phonon branch index nu here, okay? And this is a phonon polarization vector in reciprocal space, okay? And here I just show another term just for you if you are dealing with polar materials. Don't forget to include this dipole-dipole interaction term to account for long-range interactions between your atoms and the effect on the forces and the phonons. And this is just the phonon dispersion of silicon, which we are going to compute in the hands-on session. So here are some, this is my end of the presentation. Sorry if I poisoned you with a lot of maths, but I just wanted to like guide you through some basic principles of density functional theory, so you know the most important points of this historical development. And here are some very useful references. So I found this very first reference like very important because it's very pedagogical and it's designed like for PhD students if you want, and explains all the derivations or all the concepts I described here, or most of the concepts. This is basically the Bible of electronic structure theory codes. So the book by Richard M. Martin, okay, which is the basic theory of practical methods, published in 2004. And if you are interested also to phonons, you can go to this review here, or some like optical properties, the book by Bassani, and also this, I include this review here, which is also very helpful for someone who is doing his very first or her very first steps in density functional theory. So thank you for your attention, and I'm open for any questions.
Thank you for your presentation. I'm interested like the loop, because I haven't the background about the DFT calculation, but I'm interested in the loop. In my opinion, like if I understand correctly, so the DFT theory, it's about, I mean, the solution. Sorry, the solved method is like iterative method, and so I try to understand, like, for example, for the initial guess for the density, the electron density. So how do you get or how do you determine the initial guess?
That's a very subtle question. Even myself, I didn't know like 3-4 years ago. It's like, but because you know now DFT is becoming like a tool that we use without really knowing the theory behind. So people, they just get this tool and they just, you know, use it. But that's a very subtle question. I had the curiosity, what's this initial guess of DFT? And it really takes every atom inside the solid based on their positions, but they doesn't consider any interaction between the atoms, and just get the charge density of each atom separately, but at specific positions, okay? And it starts computing the charge density based on these atomic positions, okay, which is easy to do in a non-interacting picture, and then starts updating like all the other quantities that do depend on the electron density, that like the external potential, the exchange correlation functional, all these potential, the Hartree potential that we described before, then diagonalizes the Hamiltonian in reciprocal space, okay? Then you get new wave functions,
Yes.
and then you do that iteratively.
I can imagine like, but well, I'm thinking that maybe the initial guess is like what you mentioned, for the people trying, or maybe it's a impractical chosen, or depends on some others, for example, experience or maybe mathematics or physics.
Yeah, so the only input that we have when it's necessary to have for a solid or for a molecule is, just put for example, the solid, we know that experimentally silicon is a phase-centered cubic lattice. And we also have a good guess for the experimental lattice constant. So we know already that we provide the input of the atomic positions inside the unit cell. We have the unit cell, the lattice constants, okay? And then we can start the guess. Again, a molecule, we build the molecule. So if it's CO2, and we want to, model only this molecule, we know how to put CO2 in an input file to represent the positions. Then we can relax, of course, and find the good bond lengths if you want. But the initial guess is that where you put your atoms inside the unit cell, or the primitive cell, or the simulation cell, if you want.
Yeah, I got idea. And about the consistent. So the self-consistent is like, because I'm trying to mapping to the some traditional numerical, let's say the algorithm. So the
Sorry, by the way, thank you for turning on the air conditioner. Yeah, go ahead, please.
Okay.
Yeah, it was great for me. I was feeling like.
Okay. So for the self consistent is like I don't know. It's like for example, find the local minimum or the global minimum in some traditional numerical.
So it's two cases. So no, you find a global minimum. So you find a global minimum in the energy, yes, okay.
In the energy.
Based on the charge density, but it's not a global minimum that you are looking in the potential energy surface, meaning finding minima in the potential. So imagine that you have, first the DFT says that we have the wave functions which depend parametrically on the atomic positions. If you don't relax the system, so if you don't tell the code relax the system, and you just do a self-consistent field calculation with the system at those positions and those lattice constants, the system tries to find self-consistency in the charge density. So if your charge density doesn't change by a factor of like 1/1,000,000,000, then you are good. Doesn't change, so that it's converged, and you have the total energy. 1/1,000,000,000, I mean 0.00001. Okay.
Yeah. So it's
so you put you decide the threshold that you want for the convergence.
Yeah.
And as long as it doesn't change, it means that your total energy is converged with the system at this nuclear configuration.
So it's like,
but if you ask the code to relax,
yeah,
you do that all these steps iteratively. So the relaxation uses like Newton's Raphson algorithms, if you want, steep and decent methods, like, to go to a minimum in the potential energy surface. But at each step where you move the atoms, you do a self-consistent quantum cycle for the charge density.
Okay.
You see?
Yes.
So you change the atoms based on other approach, okay, to go and find a minimum in the total energy. But at each step that you change the atoms, you do a self-consistent field cycle for the charge density. You see?
Yes.
You need the total energy for this nuclei configuration. And then using like a Newton-Raphson method, if you want, to go
so it's like also
to the minimum, you start
Yeah,
moving the atoms, and you start redoing a calculation for the self-consistent field charge density.
Okay, understand. I think now I'm clear for the loop. Thank you so much.
Good. My pleasure. I think there are some questions from the chat. Could you share your screen, please? No. Thanks for the nice presentation. Regarding, that goes for Vangelis. No. Regarding the K points, you mentioned that the larger the system, the fewer K points needed. Is there a rule of thumb for calculating how many K points are needed based on the atoms in the system? So that's a good question. There is not really a rule of thumb, but it's easy for us computationally to determine the convergence. So we start with a coarse grid, let's say a grid of 3 times 3 times 3. So in previous slides, I show this like a nice brilliant zone here. I'm very proud of this figure. So here is a 4 times 4 grid, okay? So we have 16K points. Maybe the total energy of the system is not converged. So you go to 5 times 5. You start using more and more K points until you obtain convergence. And you can do that manually. So there are different convergence criteria if you want to go crazy. I have, you know, like some colleagues that they're like insane with accuracy. And they try to reach an accuracy of like, I don't know, 10 to the minus 9 or 10 to the minus 10. I think depends on what you can afford computationally. But the rule of thumb is here, just, you know, just increase your K grid and see. So you start from the unit cell, you increase your K grid. And then, for example, if your K grid is converged for a 10 times 10 grid, then if you build a supercell of that 10 times larger, then you need only the gamma point. So if you build a supercell of that 5 times larger, you need a 2 by 2 grid. Okay, I hope this answers the question. So while the electronic correlation is included in exchange correlation term, who do some material especially those containing transitional metal, need extra treatment using Hubbard U. This has something to do with localized. Yeah, you are correct. This has to do with localized orbitals, and Hubbard U parameter is introduced basically for treating those localized orbitals in this transition metal systems like efficiently, because if you use hybrids or, you know, other like approaches, this will completely fail. What the K point should be different from. Yeah, K point should be different for bulk 2D, 1, 2, 0D. We can use the same. Yeah, if it's 2D, if it's 2D, as I will show also in the tutorials, you just need 1 K point along the direction that you don't have any atoms, okay? So the direction that is perpendicular to the surface, if you want, you just need only 1 K point, and you need to sample only like the plane, the XY plane, if you want, on the surface. 1D, you just need to sample like along one direction, and 0D, I use just the gamma point. Yeah, okay. Nicola, you wanted to ask something?
Thank you.
Just wanted a clarification on the K point integration. So you said that if you have a few K points, you might not get convergence. So is it possible to get convergence but not correct convergence? Do you know? Do you understand what I mean? And so repeat the question. You might not get converged if you have fewer K points. If you have only a few K points for some specific material, you might not get convergence, right? Yes. So yeah, you need to test it. But yeah, I mean, can you get some convergence but on the wrong value if you have few K points? Okay, so can you converge your density on a wrong value, or just yeah, it's convergence. If you have okay, I got your question. So if you use a very coarse grid 2 to 2, while the converged value is 10 to 10, you'll get a charge density in any case, but the charge density will not lead you to converge properties. It's not converge the charge density with this K grid. So you need to update the K grid. The energy and the density might not match. Then everything else comes from the charge density, the energy, the forces, and everything comes from, this is the object. Density functional theory, it depends on the charge density, that everything is a functional of the density, of the electron density. And the second question, maybe a bit more deep. Out of your experience, why do we need more K points for metals or for some specific systems, and for example, organic liquids, we might not need so many? Or maybe I'm wrong, I'm not sure. No, that's correct, because, so for example, for metals, you can have the crossings like from the valence band to the conduction band. So you might need, more K points to sample, like these areas. There are the systems that, if it depends also on the property you like to study. I mean, you can also you have other systems with like very low effective masses. So this is like a very sharp parabola, and to really capture like properties in this sharp parabola, you need to really get a very huge dense grid. So all this depends on the material's properties and also on the quantity you like to compute at the end of the day. Thanks. Great. So I suggest, Spiros, we do. Yeah, Michael, sorry.
So, yeah, just the last question, Mari. Thank you very much. This is very beautiful introduction. I'm just wondering, you introduced several approximations that we have, right? So is there any way to say, either in advance or with analysis, the uncertainty, let's say, to provide an uncertainty quantification, what is the error introduced from these approximations? I mean, okay,
Like to quantify
somehow, let's say, error bars. Let's put it more practically.
I think I'll just give an example. So the answer in short is no. We cannot really quantify except if we use simpler systems and we quantify. So what I want to say to reply to this question, so for parameterizing like the hybrid fractionals and the exchange in solids, for example, or like molecules. So we depended on some calculations that they have been done on several molecules, and they just found this screening parameter of 0.25, okay? Just, which is empirical, because they found that this 0.25, and then they provided some physical reasoning, okay? Why this value, and they gave it to people. So use 0.25 for your like screening when you do hybrid fractionals for improving accuracy and including exchange in a non-interacting system, plus the correlation. And they say, okay, based on this like high throughput calculations we have done on molecules, you can use these hybrid fractionals with this screening parameter, and then you get the result. Of course, this approximation, if you get the only way to provide an error bar is to compare with experiment at the end of the day, which is actually the experiment is your many-body Schrodinger equation. So you get the result, you compare with the experiment. Sometimes you can question experiment because the experiment, they might give a bandgap value based on photoluminescence, but maybe in the experiment they have some trap or defect states and they're not sure about the bandgap. And then you come as a theorist, no, but I believe this HSC is working for this system and it gives good agreement with experiment. So I applied it on this system. I believe it should be not that big difference. Maybe you have some trap states and the experiment goes back. No, experiment comes back and say, no, you are wrong. Then we do GW, which is even more advanced for quasi-particle. Then we do BSC to include the exciton. And then we can go back to the experiment and say, no, yeah, you're right, or still look for defects. So yeah, it's an iteration. And then you start building up approximations. But our error bar is the experiment, yeah.
Yeah, but maybe just to add on that, sometimes even the experiments, not only the inaccuracies in the experiments, there might be simple different systems of the experiment. For example, you never have in a real system, you cannot have an ideal perfect crystal. This means that
yeah.
it might be the case that both numbers are correct.
Apart from the conventional pictures, like materials like silicon, gallium arsenide, which can be pristine. And
you see gold, for example, which is a very good model system experimentally. Again, there might be, very, very small defect there also. But of course, as you're right, it's a very broad topic. I think it's time for a break, huh?
Yeah. Let's do some break.
Thank you so much.
Let's do the break.
Then back in.
There is in the
Back
chat.
at 12:30.
Yeah.
No, let's do it half an hour and it's okay. I will try to do the other, like, sorry? Okay, maybe some people, they want to eat, that's the point.
So let's take a 30-minute break. There's some snacks outside for, of course, the on-site participants.
What are some methods of DFT validation? So regarding the validation of other than energy conversion, I didn't understand the question. If you could please rephrase it, because so we validate DFT results based on experimental results. It can be optical absorption, it can be a band gap, it can be, you know, like structural properties that we compare. Sorry? Or maybe, yeah, other quantum methods, but yeah, maybe someone can use. Usually to validate our computations, we do compare with experiments, yes. And then after we are confident enough that we validated a lot of experiments, we can do predictions. That's the point of DFT. So I'll leave you now for a break and we'll be back soon, okay? We still have people online? Still 30?
Yep.
Amazing. So, hello everyone. Welcome to this second session of this training event. I'd like to thank Spiros for organizing this together with other EuroCC people. So I'll just repeat some information we provided before. So I guess you all have the website, even those people online. If you don't have it, I can put it here in the chat. So you go to this website here. So there's one question, sir. Where can we get the recording link, Spiros?
Loaded on our YouTube channel. You can find the link in our website.
Yeah, okay. So this website is your guy, okay? So you select this website and you'll find all the material for the tutorial. So you go to this training event material link, put here by Spiros wisely. And here you can download all the PDFs for today's session. And now we're going to the second part of the presentation, the basics of Quantum Espresso. I'll try to be quick. So we still a little bit of time from the hands-on session, which is smaller than 2.5 hours. It will be 2 hours. So now we're gonna discuss the basics of Quantum Espresso, and we stick basically to the original time frame, let's say, okay? Yep. What I do here, hide video panel or floating meeting? Okay. Huh. Got it. So yeah, today it's the second lecture for me. We're going to talk about the basics of Quantum Espresso. As I said before in my introduction, Quantum Espresso is a code, one of the very first codes designed for density functional theory. It's open source. You can download it for free from the website of Quantum Espresso by just registering with your email and downloading the code, or from GitLab. So yeah, here is a small presentation summary. I'm going to talk about a brief introduction to the Quantum Espresso. Then I'll talk about the structure of the input files. I'll talk about the pseudo-potential approach that I didn't introduce before, plane waves, cutoff, and the spin-orbit coupling, with spin-orbit coupling being very important, especially when your system has some heavy atoms inside. Structure visualization, one of the most common tools to visualize structures is a software called Vesta. You won't use it through Cyclone, but I advise you, if you are beginning now your career in DFT computational approaches, or in general computational material science, Vesta is a very useful tool for visualizing. And you will see what input formats it can get and how to visualize the structures. We'll also guide you through a DFT band structure calculation that we will also see in the hands-on tutorials. The PB0 or HPC SCF calculation for treating the exact exchange in the system. Phone calculation, and SLARM input files, which is basically in the tutorial first page. Okay, the hands-on first page. So Quantum Espresso, it is an open source code with plane wave and pseudo-potential approach. And also it supports projected augmented wave approaches. So this POW method is mostly common in VASP commercial code, which is also the most widely used code for DFT calculations and beyond. So Quantum Espresso is a very robust tool. It exists for more than 20 years, or 30 if you want. And it relies on highly parallel linear algebra libraries, MKL, which have been tested in several high throughput systems, HPC systems, high performance computing systems like Intel, AMD, Cray, XE machines, and it has been widely used also in several Euro HPC architectures. So I have been like applied for Euro HPC or previously praised computational resources, and Quantum Espresso is one of the, widely respected codes, and people, they do understand that it scales nicely. You can do very nice scaling plots with Quantum Espresso, and convinced that your calculations will run on those systems with a good performance, okay? And here I provide, some references like regarding the structure of the code, the design of the code. And as you can see here, I list some of the citations, which in total they reach more than 40,000 citations, okay? And there are also even more, okay? So how to download and compile Quantum Espresso? So you have the slides. As I said before, you can go to the link I provided in the chat, okay? And get this PDF, and then you can just copy and paste this command if you have Git. Of course, you have Git. And then you clone into this GitHub, or you download manually, let's say, from the website. And we are going to use Quantum Espresso, the version 7.5. And then you go inside the QE directory, and then you just simply type configure, and then you make. So Quantum Espresso now, it's like the configure setup. It's very powerful. Back in the days, you had to provide a lot of things manually and explain, the configuration to the code so it can be compiled. But now, a simple configure would be like give you a very good installation. Of course, sometimes one thing that you need to do is just when you configure, you need to go to a file called makesys and just explain to the code, provide, your MKL library path for Scalapack if you want, because Scalapack will boost up the diagonalization procedure, okay? But other than that, the configure command, it's very powerful Quantum Espresso, and it can understand your system specifics. And then you can just compile by typing make -g. You can also put the number of processors for parallelized compilations. And then PW, PP, and sorry, do you have question? Oh, okay. So PW is the main module in Quantum Espresso for the self-consistent calculations to implement the Concham equations. PP here is mostly for post-processing, and PH is for phono calculations. So those are the main executables that we're gonna need for the hands-on session. So if you don't have it downloaded yet, and if you are using the code like on your own HPC or like laptop, and you can just use these commands to compile the code. And then you can also run a test to see if the compilation was successful by running this example here. So as I said, pw.x is the is the main tool in Quantum Espresso, is the main vehicle of this code. And it computes ground state density functional theory properties. It does the self-consistent field calculation. And the final output is usually the charge density. Not usually, it is the charge density. It also can print out forces and stresses. And you can also perform geometry optimization. And also you can also do band structure calculations. So computing the Concham energies of the electrons along a path, as we have shown before. CP.x is for ab initio molecular dynamics. And you can, probe the structural evolution over time, okay? pH.x, which is for phonons, for computing phonons, the electric constants, or even electrophonon matrix elements, or infrared or Raman spectra. PP is a processing tool to visualize band structures, density of states, or charge density. Neb.x, which is for Nash elastic band, to compute reaction barriers or atomic migration. Epsilon.x, which is computing the optical spectra at the independent particle theory, at the very simplest theory for optical absorption, and get the imaginary and real part of the dielectric function, absorption coefficients, everything in the independent particle approximation. It has also a PW.x, which is a very powerful code for computing electrophonocoupling through Vernier interpolation in order to go to very dense grids, because computing electrophonocoupling for dense grids is not trivial. With this code, you can do like very nice properties, compute like temperature-dependent mobilities, conductivity, superconductivity, even ultrafast dynamics, phonon line widths, or even polar ones, okay? And this CPW.x gets information about the wave functions or electrophonon matrix elements computed from PW.x or PH.x. We won't discuss about those today, but I'm just discussing the capabilities. And ZG.x, which is a code for finite temperature DFT simulations using supercells. And basically this code relies on like non-perturbative supercell approaches. So we assume that the electrons follow the nuclei diabadically, and we displace nuclei along phonons. We want to compute based on the population of the phonons at the particular temperature. We want to compute finite temperature properties, DFT finite temperature properties, and we can also compute unharmonicity and effects coming from electrophonocoupling. So the input structure of this PW.x. Here I just, in the presentation and also in the presentation I provided before, wherever you see blue apart from the equations, there is usually a link, okay? So here you just type on the link, and this will give you this website here. And here it's the website with all information about the input flux for a PW.x calculation, okay? So this is very useful. This is, if you're gonna use Quantum Espresso, this website is your guide, okay? And if you don't understand something, you can also ask ChatGPT, okay? It's always a solution, but still understand something as much as you can by the resources given from Quantum Espresso. And then you can also ask ChatGPT if something is unclear. Because ChatGPT does a Google search for you eventually, yeah? Anyway, then we go to this input structure. You have the type of calculation. So you specify to the code, we want to do a self-consistent field calculation. But here the calculation type can also be non-self-consistent. So after you got the charge density, you can run on top of that a non-self-consistent field calculation since you have the charge density and predict a property for another K point. So as we said before, in the main lecture, we use K points to sample the Brillouin zone. But then we might want a property at a different K point that was not initially computed in the charge density. So we do a non-self-consistent field calculation for a different K point, for example, and we compute the property of interest for this K point. We have a bands calculation, usually used for band structure calculations. A relaxed calculation. So if you specify that the calculation is relaxed, it basically performs a geometry optimization only for the nuclei positions, for the ions, okay? It doesn't relax the lattice parameters. But if you do VC relax, you do also relax the lattice parameters. Restart mode is just to say start from scratch, keep it from scratch, but apart, if you do a geometry optimization and you've reached to a point where you need to restart the calculation because your cluster leaves you only 10 hours to do the calculation and stops you. So you can do this restart mode if you already ran a calculation and then you want to restart it from the point where it was interrupted. Then the prefix for output files. And here is your pseudo directory, path to your pseudo potential. Pseudo potentials we didn't discuss. We're going to discuss it soon. It's one of the most important things in your calculation, and you have to choose them wisely, okay? But there are already libraries that they give you these pseudo potentials, and you can perform calculations very easily using these files. Out directory, here you specify to the code if you want to calculate and print the forces and disk input output. So the code, if you put this disk input output to high, it might print store like and print the wave functions, all of the wave functions in the system, which might take like from gigabytes to terabytes if it's a supercell, okay? So if you don't want the wave functions to use them, you typically put this disk input output to low or even none. So if you put none, it prints only the charge density and some information about the system. And then you go to the system control flag, okay? Here. So here you specify, you give the properties of the system. So iBraf equals 2, implies that your lattice is face center cubic. If you put 1, it's simple cubic. If you put BCC, it's body center cubic. So the standard, one of the standard flags that I check in PW.X is basically, I take my system based on crystallography. I know if it's FCC, BCC, simple cubic, monoclinic, hexagonal, and I go to find the correct label for iBraf, and I put it here, okay? And then we need to put the lattice parameters. You can, if you choose to use cell DM 1, 2, 3, you have to put that in Boch units, but you can also put them in angstrom if you choose A, B, C, for example. So all this information is here. It's very clear how to do it. Then you need to specify the number of atoms you are simulating. So if you have a molecule of 10 atoms, you put NAT equals 10. If you have a solid with 5 atoms, you put 5 atoms in the unit cell. Here, I just, because I will use mostly silicon today, for silicon, we have only 2 atoms inside the unit cell, okay? And this will give you, with periodic boundary conditions, will give you the solid, okay? With periodicity, let's say. So an N-tip is the number of type of atoms. So if you have cesium, lead, bromide 3, for example, you have 1 cesium, 1 lead, and 3 bromide atoms. So you put number of atoms equals 5, but N-tip you put 3, okay? If you have molecules, 10 different molecules, you put N-type 10. And then is the cutoff energy, the kinetic energy cutoff for the plane waves. So what is this pseudo potential? So as we said before, the Kohn-Sham equations, they try to solve a system of non-interacting electrons, but still, there might be a lot of electrons and they might make the problem very difficult to solve. So what we do here with the pseudo-potential approach, we say that we have the core electrons and the valence electrons. So this is simple chemistry, okay? So what's the valency of silicon, for example? Do you know? How many valence electrons the silicon atom has? Anyone from the chat? Did we get any reply on the chat, guys? Can someone check the chat? 4, yes, that's cool. So we have 4 valence electrons in silicon, okay? But there are some other electrons inside the core, okay? So what do we do here? We replace the core electrons, which do not participate essentially in chemical bonding, so they don't really interact with the other atoms, and we call them an ionic core. So we have a nucleus, which is charged by the amount of electrons, the core electrons around it, okay? And we treat it as an ionic core. And we focus only on the valence electrons, and this essentially gives us less Kohn-Sham states. And basically, with this pseudo-potential approach, we put a cutoff. So this is a figure from Wikipedia. Sorry for not acknowledging on my slide, but this is from Wikipedia. So if the red is basically the the blue is the all electron wave function, let's say the exact wave function, we put a radius, and below this radius, we define everything as core electrons. And above this, we define everything as valence electrons, let's say. And above this region, we see that we are on top of the exact all electron wave function, while below we have a smooth variation of the potential. Okay, so using this approximation makes things easier to handle and faster. Okay, and allows for more complex systems to be studied efficiently by density functional theory. So without this approximation, we wouldn't be able to go to bigger systems, surfaces, or interfaces, for example. And pseudo-potentials. So here I give some tribute to Trullier Martins, who introduced the concept of non-conserving pseudo-potentials, non-conserving in the sense that they reflect some properties, and non-conservation. Ultrasoft, which were developed by Vanderbilt, and these ultrasoft pseudo-potentials, usually they go with very low energy cutoffs, so they make the problem even faster. And optimized non-conserving Vanderbilt pseudo-potentials. Usually non-conserving pseudo-potentials are more accurate, let's say, but they come with a cost, which is the computational cost, basically. In my calculations, I usually use ONCV, but if you want to do high throughput calculations, so to study many systems, in a high throughput spirit with a particular strategy, it's better to jump to ultrasoft. But there's no rule, but it's just suggestions, because ultrasoft will be cheaper. You gain something, you lose something, so you check. Okay, and an alternative method to pseudo-potential approach is the projected augmented wave method developed in VASP, as I said before, which can be even faster. Here, I just provide in these links libraries where you can find different pseudo-potentials. So you can go to Pseudo Dojo, is the library that I use for the tutorials. And here you go this directory, you said, I want a pseudo-potential with the PBE, PBE sol, or LDA functional. So PBE is the generalized gradient approximation developed by Purtue, Brugge, and Ersnehov. And PBE sol is the PBE revised for solids, and LDA, the local density approximation. So if I have a system, let's say gallium arsenide, I go to gallium. Where is gallium? So my chemistry is very basic. So usually I just type here gallium. I type here, whoop, and I had the pseudo potential file. For the format, Quantum Espresso uses UPF, okay? So if you are using Quantum Espresso, choose UPF format, Unified Pseudo Potential format, and you have gallium pseudo potential. And then you type arsenide, and you get also arsenide. And I downloaded this for PBE. And here there are also some other versions, okay? And another thing, you can download scalar relativistic pseudo-potentials and fully relativistic. Fully relativistic is for including the effect of spin-orbit coupling, okay? I'll come to this point later. And as I said before, there are some other libraries here. So what is this plane wave energy cutoff? In principle, this Fourier sum, a Fourier series has an infinite number of parameters. The summation goes into infinite reciprocal lattice vectors G, okay? So we need a cutoff. And to decide this cutoff, we need to do a convergence test with respect to the total energy of the system. So we are increasing step by step, gradually, the cutoff until we reach convergence in the total energy. And then we said, okay, we stop at this cutoff. It can be 60 Rydberg, for example. And this cutoff will truncate the number of plane waves we are using inside the calculation. We cannot use an infinitely large cutoff because this will make the system and the diagonalization of the Hamiltonian to explode. So we need to push the cutoff to the convergence and then start doing the calculation. So if we decide the cutoff, then only these plane waves below an energy cutoff will enter. The higher the cutoff, the higher the accuracy. But if you reach convergence, the more cutoff you include, you don't get any accuracy, okay? So if it's converged, no more accuracy. If you use a low cutoff, it's faster but less accurate. And this cutoff energy, as I said before, depends on the pseudo-potential file. So if you are using ultrasoft pseudo-potentials, you need a less cutoff for convergence. And you can check the convergence by testing total energy or the forces. Then we are going to the next input section of Quantum Espresso to describe how we are going to diagonalize and solve the problem of the electrons. So here, the standard thing is to use an iterative solver for the quantum states. And this iterative solver, it doesn't just, you go in the reciprocal space, but you don't just diagonalize a big Hamiltonian matrix. You use an iterative solver, and you break the space into subspaces to solve this iteratively and efficiently, okay? And then you need a mixing mode. So go, yes, Nicole. The plane wave is this coefficient here. This is a plane wave, okay? So as I said before, if you apply Fourier series, which is a standard thing, a Fourier transform, basically, which is a standard thing in mathematics and also like in physics, go from the real space to the reciprocal space. And this is, if you type in Wikipedia Fourier transform without any plane waves or whatever, you just get this expression, okay? A similar expression, not the same one. And so we call this as a plane wave, and this is the plane wave coefficient, okay? And basically, we need to apply a cutoff because the summation here goes over all these reciprocal lattice vectors. we need to put a cutoff in the kinetic energy, which is given by this. This is the kinetic energy, okay? This is the expression for the kinetic energy. So if you decide we have a cutoff at 50 Rydberg, we stop all the reciprocal lattice vectors that are below this cutoff energy, as indicated by this figure. Other questions? Are there any other questions from the chat? Okay. But if it's related to, I can ask, if it's something about the physics or the DFT, I can answer. Okay, it's good. Okay, and then we go here. So we have the mixing mode. So the DFT, what it does to speed up the process, it basically mixes the old charge density with a mixing parameter, which is here typically given by this mixing beta, which is typically 0.3 and 0.7, with the old charge density and the new charge density. The output and the input, they give you the new charge density, okay? And then continues doing the iteration. So this is called mixing of the charge density between iterative steps, okay? And finally, we have a convergence threshold for the SCF calculation. So we say to the code, stop when you reach this convergence criterion. When you are, the ratio of the charge density is not the, it's not a ratio, but it's a metric which involves the previous and the new one. Charge density is below this value, please stop. And typical values of like 10 to the minus 10, it's a good convergence criterion, okay? Then we go to the ion dynamics. We choose our like algorithm, how to relax the dynamics, BFGS. So if you go here in this, here and you type BFGS, you use the BFGS quasi-Newton algorithm, and we said like in the presentation, you know, to do the structural relaxation. Cell dynamics. So if you choose here BFGS, you have to choose also for cell dynamics BFGS. So cell dynamics is basically for the lattice parameters, if you want, how they relax. And then you start in the atomic species. So here I use the example of silicon. We have only one atomic type. So we put silicon, we put the atomic mass and the name of the pseudo potential file. Yeah, Nicolas, go ahead. I will come to the smearing type. I guess he's talking about the occupations. I will show a few things. And mathematically, I mean, you can just, I don't have the equations here. But of course, you know, it's like very, like either it's a step function or then it starts being fractional. And you can, you know, find expressions based on the Fermi occupation, if you want, inside many books, how it's treated occupationally. Like fractional. But I will show a few things. So yes, here is the atomic species. So we have 3 types of atomic species. We put, like if we have cesium, lead, bromide, as I said before, we put cesium, lead, and bromide, the atomic masses, and the pseudo-potential file name. And then we have how we define the K-grid. So as I said before, we try to use a uniform grid. And here we put a 666 K-grid. And the 000, it's saying that we don't use any offset. So if you want to use some offset, you can turn these zeros to 1, 1, 1, but this is not. So you need to know what you are doing for introducing an offset. So typically people, they change only these 3, and depending on the structure, on your like crystallographic structure, you can find basically the number of K points and the ratio of these K points. If you do a different kind of calculation and you just don't use a uniform grid and you want to use a random grid, or you know, specify the K points you want, you need to provide like K points T by bar. Then this T by means 2 pi reciprocal lattice units, okay? 2 pi over alpha, and this is in Cartesian coordinates, okay? In units of 2 pi over alpha, where alpha is the lattice constant, this cell DM1 that we have provided here, okay? And here we give each K point explicitly in Cartesian coordinates, but in units of 2 pi over alpha, which is the lattice constant. And we also assign a weight to the K point. Why do we need to assign a weight to a K point? It's because by symmetry, some K points are related by each other. So if you are inside the Brillouin zone, and you apply one of the symmetry operations of the crystal, and you are in point X, and then you go to a point X plus delta, for example, these two K points are symmetry equivalent. And that means anything we compute for the point K point at X and anything we compute for the point at X plus D is exactly the same. So if they are exactly the same, we need to assign a bigger weight for that K point, and we don't really need to recompute it. So by enforcing the symmetries, and quantum espresso does explore the symmetries of the system, you minimize the computational problem by a bigger factor, okay? And then you have to, if you choose eventually not to use these IBRAF parameters that we have seen before, so if you don't choose to use IBRAF, so here, and you just put IBRAF 0, you're allowed to put the cell parameters manually. So here is the lattice vector alpha, here is the lattice vector beta, and here is the lattice vector C, okay? And this is how you define the structure. And finally, you need to provide the atomic position. So for silicon, we have two atoms inside the unit cell. And one lies at 0, 0, 0, and here is crystal coordinates. So it's fractional coordinates along the lattice vectors, and 0.25, 0.25, 0.25 for the other atom. As we said before, we need K points to do convergence. We have also a path gamma x gamma, if you want. Here I show in the Brillouin zone. We can explore the electronic structure along this particular path. And as we said before, if we use a bigger supercell, we just need the gamma point eventually. Here I just show how to visualize stuff. If you have Vesta installed on your laptop, I'm not requesting to have it, but when if you install Vesta at some point in your system, you can just pass these lines here like the lattice vector and put these lattice vectors here and they are fractional coordinates. So this is a format that Vesta accepts. And then when you save this information here inside the file, let's say geometry.in, and you do that, and you do Vesta geometry.in, you'll visualize the structure of silicon. As I said before, we indeed have only two atoms in the unit cell. So this is the unit cell, but Vesta will also create, some more atoms along the periodicity of the system for visualization. You can also choose to change and create an even bigger supercell. You can measure the angles with Vesta. You can measure the bond length. It's a nice tool for visualization and analysis, as the name says, visualization for electronic and structural analysis. You can also plot charge densities. Here I also plot the tetrahedra that they represent the tetrahedra coordination of silicon. Other formats can be postcard, which is a typical format for VASP, XSF, XYZ, C files, which is used from the experimentalists mostly. And with these formats, you just type Vesta, your file.cif, and you get the visualization of the structure. You can rotate the structure, you can see, you can actually visualize and get, understand what's going on there. Here I just use a typical example of a 2D material, graphene. Before I had some questions about 2D materials. And here really, I provide again, an input file like the geometry file. No, this is not an input file, so it's a geometry file for visualization in Vesta. Here you see the hexagonal lattice. So if you give this to Vesta and you change, how many unit cells to visualize, which is very easy, you'll get this hexagonal honey bomb lattice. And here you have this hexagonal coordination. And what I introduce here is it's a vacuum of 30 angstroms. Why it could be less? But why do I need a vacuum here? It's because to avoid any periodic image like interaction. So the more vacuum you have, the less the periodic image interaction. Also in the code, you can put some flags like assume isolated. So this helps, DFT codes to treat these long range effects that might have an interaction between, periodic images. So you have to also use these flags, especially when you do a DFT calculation or even the phonons. But what's the message here is that when you do 2D materials, you need to add a vacuum. Let's say your vacuum is along, the apical direction, like the vertical axis, the z-axis. You need to change this value like step by step, like in increments of like, let's say 2 angstroms, and see where it converges. If you use an infinitely large vacuum, that makes the computational load like harder, okay? So you need to find an optimum value for your vacuum if you use a 2D material, or even if you are using interfaces. So you still need to account for like the periodicity of the system and introduce a vacuum. And finally, coming to a question that we had in the Zoom. So since you don't want to probe the system along the apical direction, there is no any information, you just put one K point there, okay? And then you just explore a uniform grid along the plane, 6 times 6. Here it's another fancy system, cesium lead iodide. So here we have 5 atoms inside the unicell. We have this nice octahedra and cesium sitting at the center of the lattice, okay? And here we have iodides around a lead atom. And here we have this octahedra coordination. I'm just giving this example, so when you download Vesta and you want to play, you just copy these files, you type Vesta, you visualize the structure, and then you rotate, you play around, and you see the functionalities of Vesta. So symmetries in quantum espresso, as I said before, symmetries are important. Here so if you put verbosity equals high inside the code, usually as a PhD student, I usually had this flag on, because when you put verbosity high, it just prints you a lot of information in the output file. If you are doing high throughput calculation and you don't want to, storage data, like, which are usually the same information, you keep it verbosity too low, so you don't want a lot of outputs. But if you put too high, the code will print for you the symmetries of the system. So here it says that if you simulate graphene, the code will try to identify all the symmetries and will really find 20 symmetry operations with inversion, and 12 they have fractional translations. So this matrix is the identity, okay, which is 1, 1, 1, which is one symmetry operation. Here we have also 180-degree rotation symmetry operation. So you rotate your lattice by this symmetry operation, and then you add a fractional translation. So this symmetry operation has a rotation plus a fractional translation. So then after you do the rotation, you add also this vector here. So other rotations, they do not have fractional translations, like this 180-degree rotation along the 0, 1, 0 axis. And this information, I find it particularly useful for these systems. So yeah, then graphene is a semi-metal, and we have a Dirac cone. And coming to the question, basically, if we want to treat a semi-metal or a metal, we need to account for a smearing in the occupations. And here is basically, if you specify how the occupations are smeared, basically, and you are using a Gaussian type smearing. So you use a Gaussian smearing. So when you have crossing between valence and conduction band, and you start having fractional occupations, you need to treat them with a Gaussian smearing. And then here, d Gauss is the Gaussian parameter. And here, as I promised before, you have to also put in the code, assume isolated, because it's a 2D system, okay? Quantum espresso searches for the symmetries, as I said before, and this is very important. So if you have a high symmetry system and you want to put a 6 times 6 K point, that's 36 K points, this might be reduced down to 10 K points, actually, by taking into account the symmetries of the system. Only inversion will reduce the K points by a factor of 2 plus 1. So if you have 36 K points, that would be, with inversion, will be 19 K points. Then here I just provide also the space group, just if you are interested in symmetries. So this P means primitive lattice, 6 is for the 6-fold rotation axis, and MMM stands for mirror planes that exist in this hexagonal lattice of graphene. So here is the case of silicon. For silicon, we don't have any occupations. So it's a semiconductor. It's very clear that the valence band all the electrons, they have an occupation of 1, and in the conduction band, the occupations are 0, okay? Silicon is a very high symmetry system, has like the most symmetries that the material can have is 48. So FCC lattice, like this system, FD minus 3M, the space group 227, for example, has 48 symmetry operations with inversion, and the code will print you all the symmetries. Here, I'll just list the very first 3. Here I just also indicate what these symbols mean. You can do it as a homework, and also like if you are interested in symmetries, you can go to the crystallographic databases websites where they explain this more thoroughly and about the Wyckoff positions in the material. And like, you know, this space group is quite famous. So it's the space group of diamond, of like germanium. And the good thing is that, you know, if the materials, they belong in the same space group, what you really need to change in your inputs, it's basic for the structure, for example, it's just the atoms and the lattice parameter, okay? Then I'm coming to cesium lead iodide. One reason that I choose cesium lead iodide because it has lead, and lead is heavy, and it's a heavy atom. So like tungsten, for example, is also a heavy atom. Spin-orbit coupling plays a significant role there, and it can also lead to very like important relativistic effects on your like quantum equation and also quantum states. Yeah, I mean.
We have a question online.
Yes.
When we change the occupation to fixed for phonon calculation, what difference does it actually make?
For phonon calculation.
For phonon calculation.
PHONON.
Yes.
But I mean, are we talking for a metal? Are we talking for a semiconductor? If it's a semiconductor, occupation should be fixed to 0 and 1. If it's a metal, occupation should be fractional. And then the phonon calculation it follows what you choose for calculating the charge density.
He said for semiconductors specifically.
For semiconductors, it should be fixed. Why should we put like smeared occupations for a semiconductor?
Okay.
So it should be fixed. That's the answer.
Okay.
Okay. So spin-orbit coupling. So we put these flags inside the end system control flag. So we put L spin-orbit coupling true, non-collinear true. Okay. And we allow the system like, and we do the density functional theory calculation, the self-consistent field calculation with quantum espresso. So if you don't use these relativistic effects, your calculation might be crap, and I will show you why. So spin-orbit coupling, okay, again equations. So I'll just say like the physics here. So what is spin-orbit coupling is the interaction between an electron spin, a magnetic moment with the magnetic field produced by the orbital motion, okay? So it's the spin and the angular momentum L, basically, that are interacting, and this originates from the relativistic effects, the Dirac equation, which provides a correction, okay? So this is a correction to our Hamiltonian. Let's say this is the potential due to the nucleus. Here we have the mass of the electron, the speed of light, and the position of the electron. So we have these standard operators. I'm sure everybody who has done physics or chemistry has seen this dot product. For me, it wasn't my favorite. It was always like at the end of some courses, usually the spin-orbit coupling, and I was like, oh my God, I had too much already. Anyway, it's like here. So yeah, so this spin-orbit coupling, this term inside the Hamiltonian accounts for the energy splitting of degenerate states, okay? So as we said before, by Pauli exclusion principle, we cannot have, you know, states with the same quantum number. And here with spin-orbit coupling, we have 6 states degenerate. And, you know, by introducing this extra term in a P energy level, we have, you know, like 2 different quantum numbers, 3/2 and 1/2 because of spin up and spin down. And this, you know, they split into energy, okay? So in DFT, we use fully relativistic potentials. So as I went before in this pseudo dojo library, do I have it still open? Yeah. So here, sorry, if you want, so SR here stands for scalar relativistic, FR stands for fully relativistic, okay? So if you want to include spin-orbit coupling, you need to download a pseudo potential solved with this like a correction about spin orbit coupling, okay? Because the treatment of exchange and correlation effects, for example, is different when you account for spin orbit coupling. So if you want to use fully relativistic pseudo potentials, you have to come to this website and download the fully relativistic version that you want, okay? And here SR, FR, okay? And finally, yeah, you have to add these flags, and it's important, for example, for lead, topological insulators, bismuth, platinum, tungsten, which are like heavy atoms, and spin orbit coupling is important. Band structure calculation, so those are inputs that we have provided and we discussed before. One important thing is that for a band structure calculation, if we want to probe the conduction band, so states with occupation 0, because the semiconductor, here the example, we need to add empty states. And here I just used a crazy number of 60. So that includes many empty states. For example, if we have silicon, we have 4 valence electrons. So NBNT is equal 4. And here I have include 56 states, but this example is not silicon, it's cesium lead iodide. And because we are account for relativistic effects, and this doubles the number of electrons in the system of the valence electrons, because when you account for spin orbit coupling, you account also for the spins of the electrons, and this makes the electrons immediately twice the number of electrons that you had without spin orbit coupling. So you need to include some free bands to compute the valence band and the conduction band. Here, basically, you provide the atomic positions, and if you want to do a band structure calculation, you need to specify the path. You need to first do a self-consistent calculation with a uniform grid, and we will see that in the hands-on session. And then you put the calculation type bands, and then you compute along XRM gamma R, the electronic states along this path. And finally, here is the result about the calculation with shock and no shock. So with shock is the black line, and without spin orbit coupling is the purple line. And you see a huge difference on the electronic structure when you account for spin orbit coupling effects. Cesium lead iodide is indeed a semiconductor, okay? And without spin orbit coupling, you get a gap of 1.2 electron volts. Including spin orbit coupling, you get a very low gap of 0.06. You make it almost semi-metallic, but the experiment is at 0.78, okay? So here one naively can say, no, spin orbit coupling makes the result bad. But usually, a bad result might drive you, a bad result in the sense that doesn't agree with the experiment, might drive you to understand why you get so much worse agreement with experiment, and actually find the real reason why your gap is down there. So one reason is that exchange correlation effects. As we said before, DFT, it does some treatment to exchange correlation effects, but methods beyond that, like hybrid fractionals, they do better, okay? And another thing that we won't discuss in these tutorials and hands-on session is local disorder, where when you have a high symmetry system, in reality, the system locally is a bit disordered, okay? But on average and macroscopically, it reflects all the symmetries of the lattice, but locally is disordered. And this also, it's an effect that gives a better treatment to exchange and correlation and gives better agreement with experiment, okay? So we need to account for better treatment to exchange correlation effects in order to take this 0.06 to 1.8, around to 1.8. And actually people, they did in the literature, and they actually treat this correctly, and they found excellent agreement with experiment when you have spin orbit coupling. Without spin orbit coupling, then you are overshooting experiment, okay? And finally, if you want to do hybrid fractional calculation, you need to add these 3 flags. We'll see it in tutorial in the hands-on session. I won't go through details. I'm just saying that here we just need to put a 25 of exact exchange, and this parameter was found empirically by doing calculations on several molecules for treating the exact exchange. And as I said before, we need to just put a fraction of it because exact exchange is assuming non-interacting electrons, but in reality, electrons, they are correlated and they are interacting. So we need to put a fraction of it, okay? And you are mixing with the exchange correlation in a DFT fractional, let's say LDA or GGA. Okay, the rest it's known. And here is about how you do a phonon calculation. First, you do a self-consistent field calculation. You have your charge density, and the density functional perturbation theory that is implemented for a phonon calculation. It's this simple file. You just say, we have these masses. You have here where you store the charge density, print all the output here. Here is the dynamical matrices that we have seen before, okay? That the code will diagonalize and get the phonon frequencies and the phonon eigenvectors for each irreducible Q point. This is a convergence threshold for self-consistency. And when you put this flag through, is that you are using a uniform grid again as for the K-point grid. And here we are using a 444 grid. Most of the times it's enough, especially for pedagogical purposes, for convergence, okay? So all this is done within density functional perturbation theory. And if someone is interested, you can type this link and you can read this amazing review by Baroni et al., where they actually, this is like the Bible of phonon calculations, like published back in 2001, but still very publishable because it's so robust and it's so, like comprehensive that always people are referring to this review. Okay, so here it's the typical calculation that you'll do in the hands-on to get this phonon density of states. I won't go through details, you'll see it in the hands-on. I just here specify the path that you're gonna calculate for the silicon phonon dispersion. It's a long path, but it's nice, beautiful. And you can also check like this result compared to the literature, if it's in agreement. And basically this is the end of this like intro to quantum espresso basics, input flux if you want. And now we can proceed slowly to the tutorial if there are no, in the hands-on, if there are no questions from the audience. Yes, Nicola. That's a very nice question. Yeah. It's unlikely that they have exactly the same results so for total energy for sure, no. But maybe, like give the same electronic band structure, it might be. They might give like a slightly different band gap. The way to, choose the right pseudo potential is basically on your property of interest. So if you want to calculate band gaps and you are happy with this level of accuracy, that the ultrasoft can give you or the norm conserving can give you, and then you so if you are going to go to HSC, for example, or PBE, you have to start. I guess if I'm not mistaken, you have to start from a norm conserving pseudo potential, but that I need to double check. So it depends what you really want to do. There is no like a strategy. So of course there are cases where LDA is known to fail. There are cases that PBE might fail. There are cases that ultrasoft PBE or non-conserving PBE might not be appropriate. But the best way to do it is just to check. For me, because I don't want to bother usually with this type of question when I do the calculations, I start from the norm conserving or like ONCV. But that's my taste, okay? It's not, you should follow it. Because I know that there might be a little like more expensive, not much more expensive, but moderately more expensive. But I know they give good accuracy and they are like widely tested pseudo potentials. But of course, other people, so if Vanderbilt hears the presentation, will kill me. But of course, other people can use ultrasoft pseudo potentials. It's absolutely fine. I'm more comfortable with norm conserving. And I'm not, the expert on pseudo potentials. Other questions? For you.
Just a comment on the pseudo potentials. Maybe sometimes people treat this as hyperparameters, and they, depending on the system, they try to use the best one that represents some experimentally measured property. And then if this is the best, that they can get, then they can study other properties that experiments cannot see. So this is some procedure that might be helpful.
Yeah. I absolutely agree with this comment,
Yeah.
and that's the purpose basically of
Yes.
having these codes, and like still investing time on optimizing these codes. And another reason that I like is that having open source codes like Quantum Espresso for me helped me, to understand coding and the structure of the codes. I learned Fortran through Quantum Espresso, and and then I made my own developments, and it's a very powerful tool that can make very good predictions that can really help experiment and work hand by hand towards success. Wow. Okay, yeah. Other questions? Okay, let's go to the hands-on. Maybe